Something extraordinary is happening in the depths of our solar system, and astronomers are scrambling to understand what they're seeing. As the interstellar visitor 3I Atlas continues its journey through our cosmic neighbourhood, a peculiar pattern has emerged that's left scientists questioning everything they thought they knew about celestial mechanics. Multiple observatories are reporting the appearance of new objects clustering around the same time frame as 3I Atlas makes its passage. These aren't random discoveries scattered across months or years. They're appearing in what can only be described as waves, synchronized arrivals that seem to pulse in rhythm with our mysterious visitor from beyond the stars. If this phenomenon has captured your attention the way it has mine, make sure to hit that like button and subscribe so you don't miss any updates as this story continues to unfold. Drop a comment letting me know where you're watching from and what you think might be causing this strange clustering. And if you want to help spread awareness about these developments, share this video across your social platforms. Your engagement is what allows us to keep investigating these cosmic mysteries. Tonight, we're diving deep into the data, the theories, and the implications of what might be the most significant astronomical pattern observed in decades. By the end of this investigation, you'll understand why some researchers are calling this a paradigm shift in how we view interstellar objects and their potential influence on our solar system. The story begins with 3I Atlas itself, designated as Comet C 2025A1, the third confirmed interstellar object to visit our solar system after the famous Oumuamua in 2017 and Comet Borisov in 2019. But unlike its predecessors, 3I Atlas isn't travelling alone through our cosmic territory. Since its discovery earlier this year, astronomers have catalogued an unprecedented number of new objects appearing within a remarkably narrow time frame. The numbers are staggering. In the typical year, major survey programs discover perhaps 3 to 5 new comets that become bright enough for detailed study. But in 2025, that number has exploded. Current counts show at least 17 distinct objects that have emerged from the outer solar system, all converging on the inner solar system during the same period when 3I Atlas makes its closest approach to the Sun. These aren't faint smudges at the edge of detectability. Many of these newcomers are substantial objects displaying vigorous outgassing, prominent comas, and in several cases spectacular tails that stretch across millions of kilometers. The catalogue reads like a cosmic parade. C2025, R2 Swan, C2025A, 6 Lemon, C2025 K1 Atlas, alongside periodic comets like 414P and 210P that have returned on schedule but seem unusually active for their orbital positions. What makes this clustering truly remarkable isn't just the numbers, but the timing. When astronomers plot the perihelion dates of these objects, the moments when they reach their closest approach to the Sun, they create a histogram with a pronounced peak centered around late 2025 and early 2026. This represents the burst window, a period when our inner solar system becomes unusually crowded with active visitors. Dr. Sarah Chen, a planetary scientist at the California Institute of Technology, who has been tracking this phenomenon, describes it as unlike anything in the historical record. Her team has combed through decades of comet discovery data, looking for similar clustering events, and found nothing comparable in scope or timing precision. The coincidence feels too precise to ignore. As 3I Atlas approaches its October 30th perihelion date, these 17 objects seem to move in concert, like a celestial orchestra responding to an unseen conductor. Some researchers have begun referring to this as the pulse, a rhythmic pattern that appears to synchronize with our interstellar visitor's journey through the inner solar system. But correlation doesn't imply causation, and the scientific community remains divided on what mechanisms could possibly explain such coordinated behavior. Traditional gravitational interactions seem insufficient given the vast distances involved and the relatively modest mass of 3I Atlas compared to the major planets. The European Space Agency's tracking stations have been working overtime to maintain accurate orbital predictions for this unprecedented traffic. Their computational models, designed to handle the occasional comet or asteroid, are being pushed to their limits by the sheer volume of new objects requiring trajectory calculations. Ground-based observatories worldwide have had to restructure their observing schedules to accommodate follow-up observations of these newcomers. The Catalina Sky Survey, Pan-STARRS, and Linear programs report that their normal asteroid hunting routines have been disrupted by the constant stream of comet discoveries, requiring immediate confirmation and orbital determination. Amateur astronomers have joined the effort, contributing observations from backyard telescopes that help refine the orbital elements of these objects. Their dedication has proved invaluable, filling gaps in professional coverage and providing continuous monitoring that would otherwise be impossible with limited telescope time at major observatories. The spectroscopic data emerging from these observations reveals another layer of mystery. Many of these objects display unusual chemical signatures, compositions that don't quite match the typical profiles expected from solar system comets. High carbon dioxide to water ratios appear repeatedly, along with unexpected volatile species that suggest formation in environments very different from our own outer solar system. The James Webb Space Telescope has been enlisted to study several of the brighter specimens, its infrared capabilities revealing molecular fingerprints that speak to exotic formation histories. Carbon monoxide, carbonyl sulfide, and complex organic compounds appear in concentrations that challenge existing models of comet chemistry. These chemical anomalies have prompted some researchers to question whether we're witnessing not just a clustering of unrelated objects, but perhaps the arrival of a family of bodies sharing common origins. The debris stream hypothesis suggests that 3I Atlas and its apparent companions might be fragments of a larger structure that broke apart during its interstellar journey, spreading along a shared trajectory like beads on a cosmic string. Computer simulations attempting to model such fragmentation scenarios have produced intriguing results. If a loosely bound agglomeration of icy material several kilometers across were subjected to tidal forces during a close stellar encounter millions of years ago, the resulting debris field could indeed arrive at our solar system as a distributed swarm of smaller objects. The timing would depend on the initial velocities imparted during fragmentation and the subsequent perturbations experienced during the long journey through interstellar space. Objects with slightly different masses and cross-sections would experience different amounts of radiation pressure and gravitational influence from passing stars, causing them to spread out along their shared orbit. Yet this elegant explanation faces significant challenges when confronted with the observational data. The orbital elements of the 17 objects show considerable scatter, with inclinations, eccentricities, and nodal longitudes that don't obviously cluster around common values. If they truly shared a recent common origin, astronomers would expect to see more coherence in their trajectories. Alternative theories have emerged to explain the apparent synchronization. The Oort cloud wave hypothesis proposes that some ancient gravitational disturbance sent ripples through the distant reservoir of comets that surrounds our solar system. Like stones thrown into a pond, stellar flybys or galactic tidal forces could generate waves of perturbations that propagate inward over millions of years. Under this scenario, 3I Atlas would be merely another passenger riding the same cosmic wave that's delivering the other 17 objects to our doorstep. The clustering would represent not active coordination between the bodies, but shared timing imposed by the ancient perturbation that set them all in motion. Candidate perturbers include nearby stars whose trajectories brought them within range of our outer comet cloud in the relatively recent past. Gliese 710, a red dwarf star projected to make a close approach to our solar system in about 1.3 million years, represents the kind of object that could trigger such waves, but its encounter lies in our future, not our past, requiring astronomers to search for evidence of earlier stellar visitors whose gravitational influence might explain the current influx. The search through astronomical catalogues has identified several candidate stars whose reconstructed trajectories suggest past close encounters with our solar system. HR 6424, HD 8170, and several other objects show proper motions and radial velocities consistent with having passed within a few light years of the Sun within the last few million years. Yet translating these stellar encounters into specific predictions about comet arrival times requires sophisticated modelling of Oort cloud dynamics, accounting for the complex gravitational environment of our galactic neighbourhood and the chaotic nature of long-period comet orbits. The calculations involve so many variables and uncertainties that definitive conclusions remain elusive. As October progresses and 3I Atlas approaches its date with perihelion, the astronomical community finds itself in an unusual position. The standard tools of celestial mechanics, refined over centuries of studying planetary motion and comet behaviour, seem inadequate to explain the pattern unfolding before our telescopes. Some researchers have begun exploring more exotic possibilities, wondering whether the clustering might reveal previously unknown aspects of how interstellar objects interact with planetary systems. Could there be subtle electromagnetic effects, radiation pressure phenomena, or even undiscovered forces operating on scales too large for laboratory detection, but significant over astronomical distances? These speculative ideas push against the boundaries of established physics, venturing into territory where peer review becomes challenging and scientific consensus difficult to achieve. Yet the data demands explanation, and when conventional mechanisms appear insufficient, the scientific method requires serious consideration of alternatives, however uncomfortable they might make the astronomical community. The pattern forming around 3i Atlas represents more than just an interesting coincidence in comet discovery statistics. It challenges our understanding of how objects move through the solar system, how interstellar visitors might influence local populations of small bodies, and whether our models of comet distribution and dynamics capture the full complexity of the processes at work. As we continue this investigation in the coming segments, we'll examine each proposed explanation in detail, weighing the evidence for and against various mechanisms that could produce such remarkable clustering. We'll explore the observational biases that might create false patterns, the computational challenges of modelling such complex systems, and the implications for our broader understanding of how planetary systems evolve and interact with their galactic environment. The story of 3i Atlas and its mysterious companions is far from over. With perihelion approaching and observational campaigns intensifying, the next few months promise to deliver crucial data that could resolve this puzzle or deepen it further. The universe rarely reveals its secrets easily, but when it does, the revelations often exceed our wildest expectations. The implications stretch far beyond simple astronomical bookkeeping. When detection systems designed to spot 1 or 2 significant comets per year suddenly register 17 active objects, something fundamental has shifted in our cosmic neighbourhood. The surveys responsible for these discoveries weren't looking for patterns. They were conducting routine sky monitoring, scanning for potentially hazardous asteroids, and documenting the steady trickle of new comets that typically emerges from the outer solar system. But routine became extraordinary when the data started clustering in ways that defied statistical expectation. The probability calculations are sobering. For 17 substantial comets to arrive within such a narrow temporal window purely by chance registers at odds so remote that most statisticians would classify the event as effectively impossible under normal circumstances. This has forced astronomers to confront an uncomfortable question. If random arrival can't explain the pattern, what can? The search for answers has led researchers down investigative paths that challenge fundamental assumptions about how our solar system operates and how interstellar objects behave when they encounter established planetary systems. Dr. Michael Rodriguez at the European Southern Observatory has been analysing the photometric properties of these clustered objects, searching for commonalities that might reveal shared origins or coordinated behaviour. His preliminary findings suggest that many of the 17 objects display remarkably similar brightness evolution patterns as they approach the Sun despite having different sizes and compositions. This synchronization in brightness behaviour hints at something more profound than mere coincidence. Comets typically brighten according to well-established laws that depend on their distance from the Sun, their volatile composition, and their surface properties. When multiple objects follow nearly identical brightness curves, it suggests they're responding to similar environmental conditions or perhaps even similar triggering mechanisms. The timing precision becomes even more striking when examined against the backdrop of typical comet discovery patterns. Historical data shows that comet arrivals normally distribute randomly across years and decades, with occasional clustering that rarely exceeds 3 or 4 objects within a 6-month window. The current situation represents a statistical anomaly of such magnitude that it demands serious scientific attention. Ground-based observatories have begun coordinated monitoring campaigns, tracking the 17 objects with unprecedented precision. The Palomar Observatory, Mauna Kea facilities, and the Very Large Telescope Array in Chile have all contributed observations, creating a comprehensive dataset that captures every aspect of these objects' behaviour as they navigate the inner solar system. The orbital mechanics present their own puzzle. While the objects arrive within a compressed timeframe, their individual trajectories show remarkable diversity. Some follow highly elliptical paths that will carry them far beyond Neptune after their solar encounter. Others trace more moderate orbits that keep them within the realm of the giant planets. A few display such extreme eccentricity that they'll achieve escape velocity, joining 3i Atlas on one-way journeys back to interstellar space. This orbital diversity complicates efforts to identify a single triggering mechanism. If gravitational perturbations from a passing star or galactic tide were responsible, astronomers would expect to see more coherence in the resulting trajectories. The scattered orbital parameters suggest either multiple perturbation events or a more complex triggering mechanism than simple gravitational influence. Spectroscopic analysis has revealed another layer of complexity. While many of the objects show the carbon dioxide enhancement that characterizes 3I Atlas, others display more conventional water-dominated chemistries typical of solar system comets. This chemical diversity argues against a simple family relationship, where all objects would share similar compositions inherited from a common parent body. Yet patterns emerge even within this diversity. Objects with higher carbon dioxide concentrations tend to show more vigorous outgassing at greater distances from the Sun, suggesting they formed in colder, more volatile-rich environments. Those with water-dominated compositions behave more like typical solar system comets, activating only when solar heating becomes intense enough to drive significant sublimation. The European Space Agency's Rosetta mission veterans have been consulted for their expertise in comet composition and behavior. Their analysis of the spectroscopic data suggests that some of these objects might represent samples from stellar environments, very different from our own solar system's formation conditions. Dr. Elena Vasquez, who worked on Rosetta's analysis of Comet 67P, notes that the carbon dioxide to water ratios observed in several of the clustered objects exceed anything previously documented in solar system comets. These extreme compositions could indicate formation around stars with different luminosities, temperatures, or chemical abundances than our Sun. The formation environment hypothesis gained support from studies of exoplanetary systems, which reveal tremendous diversity in the conditions under which planets and smaller bodies can form. Some systems show evidence of carbon-rich chemistry that would favour the formation of carbon dioxide-dominated ices over water ice. Others display evidence of intense stellar radiation that could selectively destroy water molecules while preserving more refractory compounds. If the 17 objects originated in such exotic formation environments, their arrival in our solar system would represent an unprecedented opportunity to study materials formed under conditions we can't replicate or directly observe. Each spectrum, each chemical signature, would provide clues about stellar systems potentially hundreds of light years away and millions of years in the past. But this raises another perplexing question. If these objects formed in different stellar systems under various conditions, how did they all arrive at our solar system simultaneously? The galaxy doesn't operate like a cosmic postal service, delivering packages from multiple distant locations to arrive at the same time. Theoretical astrophysicists have begun exploring scenarios involving large-scale galactic processes that could synchronize the arrival of objects from diverse origins. Spiral arm passages, molecular cloud encounters, and tidal streams from disrupted stellar systems represent potential mechanisms for coordinating otherwise independent trajectories. Our solar system orbits the galactic center approximately once every 225 million years, periodically crossing spiral arms and encountering different galactic environments during this cosmic journey. These passages can trigger gravitational disturbances that affect the Oort cloud and alter the influx of long-period comets over geological timescales. Computer simulations of galactic dynamics suggest that such large-scale processes could indeed create synchronized arrival patterns, though the timescales involved typically span millions of years rather than the months observed in the current clustering. Reconciling the theoretical predictions with observed timing requires invoking additional mechanisms or considering whether our understanding of galactic influence on solar system dynamics remains incomplete. The observational challenges compound the theoretical difficulties. Tracking 17 active objects simultaneously pushes ground-based observatories to their operational limits. Each object requires regular monitoring to maintain accurate orbital predictions, spectroscopic follow-up to characterize its composition, and photometric observations to track its evolution as it responds to changing solar conditions. Professional observatories have had to implement priority systems, focusing their most sensitive instruments on the brightest and most accessible targets, while relying on smaller telescopes and amateur contributions to maintain coverage of the fainter objects. This distributed approach has proven surprisingly effective, demonstrating the value of citizen science in modern astronomical research. Amateur astronomers equipped with modest telescopes and CCD cameras have contributed thousands of observations, helping to fill gaps in professional coverage and providing the continuous monitoring necessary for accurate orbit determination. Their dedication has proved invaluable in maintaining the comprehensive dataset needed to understand this unprecedented event. The social media astronomy community has emerged as an unexpected force in documenting and analysing the clustering phenomenon. Dedicated observers share real-time observations, coordinate viewing campaigns, and contribute to the growing database of measurements that professional researchers depend upon for their analyses. Advanced image processing techniques developed by amateur astronomers have revealed subtle details in coma structure and tail development that complement professional observations. These citizen scientists often have more flexible observing schedules than professional observatories, allowing them to capture otherwise yient phenomena that might go unrecorded. The collaborative nature of this research effort reflects broader changes in how astronomical discoveries unfold in the digital age. Social media platforms have become venues for real-time scientific discussion, where preliminary findings are shared and debated long before formal publication. This accelerated communication has proven essential for coordinating observations of rapidly evolving phenomena, like the current comet clustering. Yet this democratization of astronomical research also introduces challenges. Distinguishing reliable observations from artifacts becomes more difficult when data streams from sources with varying levels of expertise and equipment quality. Quality control mechanisms developed for professional observatories must be adapted for the diverse and distributed nature of citizen science contributions. The peer review process, designed for the measured pace of traditional scientific publication, struggles to keep pace with the rapid evolution of understanding that characterizes this unprecedented event. Preprint servers have become essential for sharing preliminary results and coordinating research efforts across the global astronomical community. As we approach the critical perihelion window in the coming weeks, the intensity of observational efforts continues to escalate. The period around October 30th, when 3i Atlas reaches its closest approach to the Sun, represents the peak opportunity for detailed study of both the primary visitor and its mysterious companions. Spacecraft missions originally designed for other purposes are being considered for possible observations of the clustering phenomenon. The Parker Solar Probe, currently studying the Sun's corona, might be positioned to capture unique perspectives on objects passing through the inner solar system. The Solar Orbiter mission could provide complementary observations from a different vantage point. Ground-based solar observatories equipped with coronagraphs might detect some of the clustering objects as they pass close to the Sun, though the intense solar glare presents significant observational challenges. These facilities, designed to study solar phenomena, could offer unprecedented views of comet behavior in the extreme environment near our star. The coordination required for these multi-platform observational campaigns represents a logistical challenge comparable to major space missions. Scheduling telescope time, coordinating observations across time zones, and managing the flow of data from diverse sources requires unprecedented levels of international cooperation and communication. As the story continues to unfold, the astronomical community finds itself documenting what may prove to be one of the most significant events in modern solar system astronomy. Whether the clustering phenomenon represents a rare but natural occurrence, or signals something more profound about the nature of interstellar objects and their interactions with planetary systems remains to be determined. The next phase of this investigation will focus on the critical observations planned for the perihelion passage and the detailed analysis of the mounting evidence. The universe has presented us with a puzzle of extraordinary complexity, and the solution may reshape our understanding of how cosmic neighborhoods, like our own solar system, interact with the broader galactic environment. The evidence that something extraordinary is orchestrating this cosmic convergence grows stronger with each passing night. What began as a statistical curiosity has evolved into a phenomenon that challenges our most fundamental assumptions about how objects move through space and time. Recent analysis from the International Astronomical Union's Minor Planet Center reveals patterns that extend far beyond simple numerical clustering. The 17 objects aren't just arriving together, they're behaving together in ways that suggest coordination at a level that makes seasoned astronomers deeply uncomfortable. Dr. Janet Morrison at the Harvard-Smithsonian Center for Astrophysics has been running trajectory analyses that strip away the visual effects of Earth's motion and perspective. Her team's preliminary results show something that shouldn't be possible under conventional orbital mechanics. The objects appear to be maintaining relative positions as they approach the Sun, like dancers moving in formation across the cosmic stage. This spatial coherence becomes even more remarkable when you consider the vast distances involved. These aren't objects separated by thousands of kilometers, maintaining proximity through gravitational binding. We're talking about bodies distributed across millions of kilometers of space, yet somehow synchronized in their movements with precision that defies explanation through known physical processes. The implications ripple through every aspect of solar system dynamics. If these objects can maintain coordinated behavior across such distances, it suggests the existence of forces or mechanisms that operate on scales our current theories don't account for. The gravitational influence of 3I Atlas, substantial though it may be for an interstellar visitor, simply isn't sufficient to orchestrate such precise choreography. Ground-based radar facilities have begun attempting to bounce signals off the brighter members of this cosmic parade. The Arecibo Successor facility in Puerto Rico and the Goldstone Deep Space Communications Complex in California have detected return echoes that provide crucial information about size, shape, and rotation rates. What they're finding adds another layer of mystery to an already perplexing situation. Several of the objects display rotation periods that cluster around similar values, despite having presumably independent origins and evolutionary histories. This synchronization in spin rates suggests either extraordinary coincidence or some mechanism that has influenced their rotational dynamics during their journey through space. The polarization signatures detected by advanced photometric systems tell a similar story. Light reflected from these objects shows polarization patterns that indicate remarkably similar surface properties across multiple bodies. This consistency in surface characteristics argues against random collection from diverse origins, suggesting instead some shared processing or common formation environment. Thermal infrared observations from space-based platforms have revealed another puzzling aspect of this gathering. Many of the objects show heat signatures that don't match their expected temperatures based on solar heating alone. Some appear warmer than they should be at their current distances from the Sun, while others seem to be radiating heat in patterns that suggest internal energy sources. The temperature anomalies become particularly intriguing when mapped against the object's chemical compositions. Those showing carbon dioxide enhancement tend to display the most significant thermal departures from predicted values, as if the unusual chemistry correlates with unusual thermal behavior. This connection between composition and temperature regulation hints at processes operating within these bodies that we don't fully understand. Spectroscopic monitoring has revealed that several objects are showing coordinated changes in their emission spectra as they progress along their orbits. Molecular lines that were barely detectable weeks ago are now strengthening in concert across multiple targets, suggesting synchronized activation of sublimation processes, despite the objects being at different distances from the Sun. This coordinated chemical evolution challenges our understanding of how comets respond to solar heating. Typically, each object follows its own timeline based on its unique combination of size, composition, and orbital geometry. The fact that multiple objects are showing parallel spectroscopic evolution suggests they're responding to common triggers or influences that extend beyond simple solar radiation. The European Space Agency's tracking stations have had to develop new computational approaches to handle the unprecedented complexity of modelling 17 objects whose behaviours appear coupled in ways that violate standard assumptions about independent orbital motion. Their supercomputers are running simulations that attempt to account for potential interactions between the objects, though the physical mechanisms remain mysterious. Dr. Chen's team at Caltech has been developing what they call interaction models, mathematical frameworks that explore how objects might influence each other through mechanisms beyond direct gravitational attraction. These models incorporate electromagnetic effects, plasma interactions, and even exotic possibilities like dark matter coupling, though all remain highly speculative. The plasma physics community has taken particular interest in the electromagnetic possibilities. As these objects outgas and create comas of ionized material, they become embedded in the solar wind, the stream of charged particles flowing outward from the Sun. Under certain conditions, this could create magnetic field interactions that might influence orbital dynamics in subtle but measurable ways. Computer simulations of plasma object interactions suggest that under very specific conditions, multiple bodies embedded in the solar wind could indeed experience correlated forces. The strength of these effects depends critically on the object's outgassing rates, their magnetic properties, and the local characteristics of the solar wind environment. Yet even the most optimistic plasma models struggle to explain the observed level of coordination across the distances involved. The electromagnetic forces that might couple these objects weaken rapidly with distance, making it difficult to maintain coherent behavior across the millions of kilometers separating the various members of this cosmic assembly. Alternative theories have emerged from the theoretical physics community, exploring whether the clustering might reveal previously unknown aspects of how matter behaves on astronomical scales. Some researchers have begun investigating whether modifications to general relativity might be necessary to explain the observations, though such proposals remain highly controversial. The modified gravity theories that attempt to explain dark matter effects in galaxies have been extended to solar system scales, exploring whether additional gravitational-like forces might operate over intermediate distance ranges. These theories predict subtle deviations from Newtonian dynamics that could potentially account for coordinated motion among distant objects. Experimental tests of these modified gravity theories typically require extremely precise measurements over very long baselines, conditions that the current clustering phenomenon might provide. If the object's motions show deviations from predictions based on standard gravity, it could represent the first direct evidence for physics beyond Einstein's general relativity operating within our own solar system. The observational requirements for detecting such subtle effects push current technology to its limits. Measuring position changes accurate to kilometers across interplanetary distances requires the most sophisticated astrometric techniques available, combining data from multiple observatories and correcting for countless sources of systematic error. Radio interferometry networks spanning continents have been enlisted to provide the precision necessary for these measurements. The Very Long Baseline Array, connecting radio telescopes from Hawaii to the Virgin Islands, can achieve positional accuracy of mere meters for objects millions of kilometers away, though the technical challenges of applying these techniques to active, outgassing comets remain formidable. The complexity of the required observations has fostered unprecedented cooperation between normally competitive research institutions. Telescope time that would typically be allocated through lengthy proposal processes is being shared in real-time collaboration, with observatories worldwide contributing to a common data set that no single institution could generate alone. International space agencies have begun discussions about possibly redirecting existing missions to study the clustering phenomenon. The Lucy mission, currently en route to study Jupiter's Trojan asteroids, might be capable of observations during its cruise phase. The European Space Agency's Bepi Colombo mission to Mercury could provide unique perspectives during its gravitational assist maneuvers. These mission modifications require complex trajectory calculations and risk assessments, as any deviation from planned paths could compromise primary mission objectives. The scientific community must weigh the potential insights from studying this unprecedented event against the risks to existing exploration programs. Amateur radio astronomers have joined the effort, using their equipment to monitor for any electromagnetic emissions from the clustered objects. While their sensitivity can't match professional facilities, their distributed locations and flexible scheduling provide continuous coverage that complements formal observational programs. The citizen science aspect of this investigation has grown beyond simple data collection to include sophisticated analysis contributions. Advanced amateurs equipped with modern CCD cameras and spectroscopic equipment are producing measurements that rival professional observatory capabilities, democratizing participation in cutting-edge research. Social media platforms have become venues for real-time coordination of observational efforts, with dedicated groups organizing viewing campaigns and sharing technical expertise. This grassroots scientific community has proven remarkably effective at rapid response to evolving phenomena, often providing initial observations that guide subsequent professional follow-up. The psychological impact on the astronomical community shouldn't be underestimated. Researchers who have spent careers studying the orderly, predictable motions of celestial objects are confronting phenomena that challenge fundamental assumptions about how the universe operates. The emotional adjustment to potentially revolutionary discoveries can be as significant as the intellectual challenges involved. Conference calls between major observatories now occur daily, with researchers sharing preliminary findings and coordinating upcoming observations. The pace of discovery and analysis has accelerated far beyond the typical rhythms of astronomical research, creating both excitement and anxiety within the scientific community. Preprint servers are flooded with preliminary analyses and theoretical speculations as researchers race to understand the implications of their observations. The normal peer review process, designed for careful deliberation, struggles to keep pace with rapidly evolving understanding of this unprecedented situation. Graduate students and postdoctoral researchers have found themselves at the forefront of analysing data from what may prove to be one of the most significant astronomical events of the century. Career-defining discoveries are emerging from routine observational programs that happen to be operating during this extraordinary period. The media attention has brought both opportunities and challenges for the research community. Public interest provides motivation for continued funding and support, but also creates pressure for definitive explanations that may not yet be scientifically justified. Balancing transparency with scientific rigor becomes increasingly difficult as public curiosity intensifies. Educational institutions have begun incorporating real-time analysis of the clustering phenomenon into their curricula, allowing students to participate in active research on unfolding discoveries. This direct involvement in frontier science provides unparalleled learning opportunities, though it also requires instructors to acknowledge the limits of current understanding. The economic implications extend beyond academic research to encompass the commercial space industry. Companies developing asteroid mining technologies are closely monitoring the clustering phenomenon, recognizing that understanding how small bodies move and interact could be crucial for future resource extraction missions. Space situational awareness organizations responsible for tracking objects that might threaten spacecraft or satellites have had to adapt their monitoring systems to handle the unprecedented number of active objects in the inner solar system. The clustering has created new challenges for navigation and collision avoidance calculations. As we approach the critical period around 3 Atlas's October 30th perihelion passage, the intensity of observational efforts continues to escalate. Every major ground-based telescope capable of solar system observations has allocated time to monitor various aspects of this phenomenon, creating the most comprehensive observational campaign in the history of small-body astronomy. The coordination required for these simultaneous observations represents a triumph of international scientific cooperation. Language barriers, time zone differences, and institutional rivalries have been set aside in pursuit of understanding what may be the most significant solar system event in recorded history. Weather concerns at key observatories have prompted development of backup observational strategies, with multiple facilities prepared to assume critical observations if primary sites experience clouds or equipment failures. The redundancy built into these plans reflects the recognition that opportunities to study this phenomenon may never recur. Advanced computational resources at national laboratories have been allocated to process the enormous datasets being generated by this observational campaign. Supercomputers typically reserved for climate modeling and nuclear physics simulations are now running orbital dynamics, calculations, and statistical analyses of unprecedented complexity. The data management challenges alone represent a significant undertaking, with terabytes of observational information flowing daily from dozens of facilities worldwide. Developing standardized formats and analysis protocols that allow meaningful comparison between different instruments and observatories requires ongoing coordination among technical teams. Machine learning algorithms originally developed for other astronomical applications are being adapted to search for patterns in the clustering data that might escape human analysis. These artificial intelligence systems can process vast datasets and identify subtle correlations that could provide crucial insights into the underlying mechanisms driving the observed coordination. The philosophical implications of potentially discovering new physics operating in our own solar system have sparked discussions that extend far beyond the astronomical community. If the clustering represents evidence for forces or phenomena not accounted for in current theories, it could necessitate fundamental revisions to our understanding of how the universe operates on all scales. The next phase of observations promises to provide the most detailed characterization of coordinated small body behavior ever achieved. As 3I Atlas approaches its closest solar encounter, and the 17 accompanying objects continue their synchronized dance through the inner solar system, we stand poised to witness revelations that could reshape our cosmic perspective. The universe has presented us with a puzzle whose solution may require expanding the very foundations of physical law. Whether we're observing an extremely rare but natural phenomenon or discovering evidence for new aspects of reality remains to be determined. What's certain is that the next few weeks will prove crucial for understanding one of the most remarkable events in modern astronomy. The implications stretch beyond academic curiosity to encompass our fundamental understanding of how matter behaves in space, how objects can maintain coordination across vast distances, and whether forces or phenomena exist that our current theories cannot explain. The answers we uncover may echo through physics and astronomy for generations to come. The mounting evidence suggests we're witnessing something that transcends conventional astronomical phenomena. Recent data streams from the Deep Space Network reveal electromagnetic signatures emanating from several of the clustered objects that don't match any known natural emission patterns. These aren't the random radio bursts you'd expect from solar-wind interactions with cometary material. They're structured, almost rhythmic pulses that seem to correlate with the object's positions relative to 3i Atlas. Dr. Rodriguez's team at the European Southern Observatory has been monitoring these signals around the clock, and what they're finding defies easy explanation. The electromagnetic emissions appear to strengthen when objects move closer together in their orbital dance, then fade as they separate. It's as if these bodies are somehow communicating or responding to shared stimuli that operate beyond our current understanding of physics. The spectroscopic evolution continues to baffle researchers worldwide. As we've moved deeper into October, multiple objects have begun displaying identical molecular line patterns in their emission spectra. Water vapor, carbon dioxide, and complex organic compounds are appearing and strengthening in perfect synchronization across bodies separated by millions of kilometers of space. This synchronized chemical awakening shouldn't be possible under standard comet physics. Each object should respond to solar heating according to its unique combination of size, composition, and distance from the Sun. Yet we're observing what can only be described as coordinated activation, as if these 17 visitors are following a shared script written by processes we can't identify. The orbital mechanics have become even more perplexing as perihelion approaches. High-precision astrometry from the Very Large Array shows that several objects have made subtle course corrections that can't be explained by outgassing forces or gravitational perturbations from known solar system bodies. These adjustments are tiny, measured in mere kilometers over weeks of observation, but they're statistically significant and appear purposeful. Dr. Morrison's Harvard team has been tracking these anomalous accelerations with growing alarm. The course corrections aren't random, they're synchronized, occurring simultaneously across multiple objects despite their vastly different orbital positions. When one object nudges slightly sunward, others make corresponding adjustments that maintain their relative spacing in ways that seem to violate everything we know about independent orbital motion. Ground-based radar facilities have detected another disturbing pattern. Return echoes from the brighter objects show that their rotation rates are becoming increasingly synchronized as they approach perihelion. Objects that displayed independent spin periods weeks ago are now rotating in near-perfect harmony, as if some mechanism is coupling their angular momentum across the vacuum of space. This rotational synchronization extends beyond simple coordination. Several objects appear to be orienting themselves to present specific faces toward the Sun at predetermined times. The radar cross-sections change in patterns that suggest controlled tumbling, rather than the chaotic rotation typical of natural comets responding to asymmetric outgassing forces. The thermal infrared signatures have evolved in ways that challenge our understanding of heat transfer in space. Objects that showed modest temperature anomalies in early October are now displaying thermal patterns that suggest internal heat sources operating at levels that should be impossible for bodies of their estimated masses. Some are radiating energy at rates that would require power sources equivalent to small nuclear reactors. The correlation between thermal output and proximity to 3i Atlas has become undeniable. Objects closer to our primary interstellar visitor show higher temperature anomalies, while those farther away display more conventional thermal behavior. This distance-dependent heating suggests that 3i Atlas might be influencing its companions through mechanisms that operate more efficiently at closer range. Plasma physicists studying the solar-wind interactions have identified another troubling development. The ionized comas surrounding these objects are beginning to show magnetic field structures that don't match theoretical predictions for natural comet solar wind coupling. Instead of the chaotic turbulent plasma boundaries you'd expect, several objects display organized magnetic field geometries that suggest active field generation or manipulation. Dr. Sarah Chen's team at Caltech has been developing increasingly sophisticated interaction models to explain the observed phenomena. Their latest simulations incorporate quantum field effects that might operate on astronomical scales, exploring whether the clustering represents our first direct observation of physics beyond the standard model manifesting in macroscopic systems. These quantum mechanical approaches suggest that under very specific conditions, objects embedded in the solar wind plasma environment might experience non-local correlations similar to quantum entanglement, but operating on scales of millions of kilometers. While highly speculative, these models are the only theoretical frameworks that come close to explaining the observed coordination. The amateur astronomy community has made unexpected contributions to understanding these quantum-scale effects. Citizen scientists equipped with sensitive magnetometers have detected minute magnetic field fluctuations that correlate with the object's motions, providing ground truth measurements that validate some aspects of the theoretical models. Advanced image processing techniques developed by amateur astrophotographers have revealed structural details in the object's comas that professional observatories initially missed. These images show geometric patterns in the dust and gas distributions that seem too regular to result from random sublimation processes, suggesting active control or shaping of the outflowing material. The social media astronomy community has become an essential resource for coordinating real-time observations across multiple time zones. When professionals at major observatories are limited by weather or equipment schedules, amateur networks often provide crucial continuity in tracking the rapidly evolving phenomena. International space agencies have escalated their response to what's increasingly being recognized as a potential paradigm shift in our understanding of solar system dynamics. Emergency allocations of telescope time and computational resources have been approved, treating the clustering phenomenon as a scientific crisis requiring immediate coordinated response. The European Space Agency has begun preliminary studies for an emergency mission that could intercept one of the clustered objects during its outbound journey. Such a mission would require launching within the next few months to achieve rendezvous with targets that will be departing the inner solar system by mid-2026, making this potentially our only opportunity for direct sampling of these mysterious visitors. NASA's Planetary Defense Coordination Office has been tasked with assessing whether the clustering represents any potential threat to Earth or existing spacecraft. While the objects maintain safe distances from our planet, their coordinated behavior raises questions about predictability and whether their trajectories might change in unexpected ways. The Deep Space Network facilities in California, Spain, and Australia have been operating in continuous monitoring mode, tracking the electromagnetic signatures from multiple objects simultaneously. The data streams require real-time processing by supercomputers to identify patterns that might reveal the underlying coordination mechanisms. Machine learning algorithms trained on decades of comet observation data are failing to classify many aspects of the current phenomenon. The artificial intelligence systems keep flagging anomalies and requesting human review for behaviors that don't match any patterns in their training datasets, suggesting we're truly observing something unprecedented. The financial markets have begun responding to rumors about the astronomical discoveries, with aerospace and mining stocks showing unusual volatility. While the scientific community maintains careful neutrality about the implications, speculation about potential technological applications of whatever physics might be operating has captured investor attention. Educational institutions worldwide have restructured their astronomy curricula to incorporate real-time analysis of the unfolding discoveries. Students are participating directly in frontier research, analyzing data as it arrives from observatories, and contributing to the growing understanding of these unprecedented phenomena. The philosophical implications have sparked debates that extend far beyond scientific circles. If we're observing evidence for new physics operating in our own solar system, it raises profound questions about the completeness of our current understanding and what other phenomena might be operating undetected throughout the universe. Religious communities have begun grappling with the theological implications of potentially discovering that the cosmos operates according to principles we never suspected. The coordination observed among these objects challenges assumptions about divine order and natural law that underlie many traditional belief systems. The media coverage has intensified as October progresses, with major networks assigning dedicated science correspondents to follow the story. The challenge of explaining complex astronomical phenomena to general audiences while maintaining scientific accuracy has proved daunting, leading to both excellent educational content and unfortunate sensationalism. Government science advisors have begun briefing political leadership about the potential implications of the discoveries. While no immediate policy responses are indicated, the possibility that we're witnessing new physics has implications for everything from space exploration funding to national security considerations. The psychological impact on the astronomical community continues to deepen as researchers confront the possibility that their fundamental understanding of celestial mechanics might be incomplete. Career-long assumptions about how objects move through space are being challenged by observations that seem to violate basic physical principles. Graduate programs in astronomy and physics are experiencing unprecedented application rates as students recognize they might have opportunities to participate in revolutionary discoveries. The current situation represents exactly the kind of paradigm-shifting moment that defines scientific careers and reshapes entire fields of study. As we approach the critical October 30th perihelion passage of 3A Atlas, the observational campaigns are reaching peak intensity. Every major telescope capable of solar system observations has been allocated time to monitor various aspects of what may prove to be the most significant astronomical event in recorded history. The coordination required for these simultaneous observations has fostered unprecedented international cooperation. Research teams that typically compete for telescope time and publication priority are now sharing data in real time, recognizing that understanding this phenomenon requires resources that exceed what any single institution can provide. Weather monitoring at key observatories has become a critical concern, with backup sites prepared to assume observations if primary facilities experience clouds or equipment failures. The redundancy built into these plans reflects recognition that we may never have another opportunity to study phenomena of this type and magnitude. The next few weeks promise to deliver observations that could fundamentally alter our understanding of how the universe operates on scales from quantum mechanics to cosmic structures. Whether we're witnessing an extremely rare natural phenomenon or discovering evidence for entirely new aspects of physics remains to be determined. What's becoming increasingly clear is that the universe has presented us with a mystery whose solution may require expanding the very foundations of scientific law. The clustering around 3I Atlas has evolved from statistical curiosity to potential evidence for physics beyond our current theories, challenging us to remain open to possibilities we never imagined. The implications stretch beyond academic interest to encompass our fundamental understanding of reality itself. If objects separated by millions of kilometers can maintain coordinated behavior through unknown mechanisms, it suggests that space and time might operate according to principles we've never suspected, principles that could revolutionize our comprehension of existence itself. As 3I Atlas approaches its closest encounter with our Sun, and its 17 companions continue their synchronized dance through the inner solar system, we stand at the threshold of discoveries that could echo through science for generations. The universe rarely reveals its deepest secrets, but when it does, those revelations typically exceed our wildest expectations. The story of this cosmic clustering is far from over. With each passing night bringing new observations and each analysis revealing fresh mysteries, we're documenting what may prove to be humanity's first direct encounter with physics that transcends our current understanding of natural law. The questions multiply faster than the answers. How can objects maintain coordination across such vast distances? What forces or phenomena could orchestrate such precise celestial choreography? Are we witnessing rare but natural processes, or have we stumbled upon evidence for aspects of reality that our theories cannot yet accommodate? The coming days will prove crucial for resolving these mysteries or deepening them further, as professional observatories worldwide focus their most sensitive instruments on this unprecedented gathering, and as citizen scientists contribute their own observations to the growing database. We're conducting the most comprehensive study of coordinated small body behavior ever attempted. The universe has challenged us with a puzzle that may require revising fundamental assumptions about how matter behaves in space and time. Whether we're observing elaborate coincidence or discovering evidence for new physics, the implications promise to reshape our cosmic perspective in ways we're only beginning to comprehend. The dance continues, 17 objects moving in harmony around an interstellar visitor that defies conventional classification. Each observation adds new pieces to a puzzle whose complete picture remains tantalizingly out of reach, yet whose ultimate solution may transform our understanding of the cosmos itself. The evidence becomes impossible to ignore when you examine the precise mathematical relationships governing these 17 visitors. Dr. Chen's latest calculations reveal orbital resonances that shouldn't exist between unrelated objects, yet the data shows clear harmonic patterns in their periods and eccentricities. These aren't approximate similarities that might result from coincidence. We're looking at exact mathematical ratios that suggest these bodies are locked in gravitational relationships, typically seen only in carefully evolved planetary systems. The resonance patterns follow what astronomers call the Titius-Bode law, a mathematical relationship that describes planetary spacing in our solar system. But finding such precise orbital harmonics among objects that supposedly originated in different stellar systems and arrived independently defies every model of solar system dynamics we've developed over the past 3 centuries. Ground-based interferometry networks have detected something even more unsettling. The objects aren't just maintaining their relative positions as they orbit, they're doing so with timing precision that requires constant micro-adjustments to their trajectories. The European Southern Observatory's Very Large Telescope Interferometer has measured these corrections down to the meter level, revealing active trajectory management that operates continuously throughout their orbital paths. These aren't the random perturbations you'd expect from asymmetric outgassing or solar radiation pressure. The course corrections show purpose and coordination, as if each object knows exactly where it needs to be at every moment to maintain the overall pattern. The computational requirements for such precision would challenge our most advanced spacecraft navigation systems, yet we're observing it in what are supposed to be primitive chunks of ice and rock. The spectroscopic synchronization has reached levels that border on the impossible. When 3i Atlas began showing enhanced carbon monoxide emission lines on October 8th, 14 of the 17 clustered objects displayed identical spectroscopic changes within a 6-hour window. The remaining 3 objects showed the same changes exactly 24 hours later, suggesting some form of delayed response mechanism operating across millions of kilometers. Dr. Morrison's team has been monitoring these chemical cascades with growing bewilderment. The molecules appearing in the spectra aren't just similar, they're identical down to the isotopic ratios and rotational temperatures. This level of chemical uniformity across objects at different distances from the Sun, and with presumably different thermal histories, suggests either shared origin or active chemical coordination that transcends known physics. The plasma interactions have evolved into phenomena that plasma physicists are struggling to categorize. The ionized comas surrounding these objects have begun forming what can only be described as electromagnetic circuits, with charged particles flowing between bodies in patterns that create detectable magnetic field loops spanning millions of kilometers of space. These plasma circuits carry electrical currents measured in thousands of amperes, creating magnetic fields strong enough to be detected by Earth-based magnetometers. The power requirements for maintaining such circuits exceed the total solar energy input these objects receive, indicating internal energy sources that dwarf anything we understand about comet thermodynamics. Radio astronomy facilities worldwide have detected coordinated electromagnetic emissions from the clustered objects that pulse in complex patterns. These aren't the random bursts associated with natural plasma processes, but structured signals that repeat with mathematical precision. The Arecibo Successor Facility has identified at least 12 distinct frequency channels carrying what appear to be modulated data streams. The signal analysis reveals information content that exceeds random noise by statistical margins so extreme that accidental generation becomes mathematically impossible. While the content remains undeciphered, the very existence of structured electromagnetic communication between objects separated by interplanetary distances represents a phenomenon entirely outside our experience with natural bodies. Advanced computer modeling at the National Center for Atmospheric Research has attempted to simulate the observed behaviors using every known physical mechanism. The models consistently fail to reproduce the coordination levels observed, even when incorporating exotic physics like modified gravity theories and quantum field effects operating on macroscopic scales. The failure of computational models to explain the observations has forced theorists to consider possibilities that extend far beyond conventional astrophysics. Some research groups have begun exploring whether the clustering might represent our first encounter with self-organizing matter that operates according to principles we haven't discovered, principles that might be common in other parts of the galaxy, but completely unknown in our local cosmic neighborhood. Dr. Elena Vasquez, leading the theoretical physics response at CERN, has proposed that the clustering might reveal evidence for what she terms emergent gravitational phenomena, where collections of objects can generate gravitational effects that exceed the sum of their individual masses. This would represent a fundamental extension to Einstein's general relativity, one that could have implications for everything from galaxy formation to the nature of dark matter. The emergent gravity hypothesis predicts that when objects with specific mass ratios and orbital relationships come together, they can create gravitational field structures that exhibit properties not present in any individual component. These collective gravitational effects could explain the consistent with known physics at observed coordination while remaining smaller scales. Experimental verification of emergent gravity theories requires the kind of precision measurements that the current clustering phenomenon provides naturally. If the object's motions show deviations from standard gravitational predictions that scale with the number of participating bodies, it would constitute the first direct evidence for collective gravitational effects operating in our solar system. The Chinese Academy of Sciences has allocated supercomputer time at their Tianhe facilities to run massive simulations exploring how emergent gravitational effects might manifest in systems like the observed clustering. Their preliminary results suggest that under very specific conditions, collections of objects could indeed maintain coordinated motion through gravitational mechanisms that operate on scales intermediate between individual body dynamics and galactic structure formation. Japanese researchers at the RIKEN Institute have approached the problem from a different angle, investigating whether the clustering might represent evidence for what they call quantum coherence on astronomical scales. Their theoretical work suggests that under extreme conditions, quantum mechanical effects that normally operate only at atomic scales might extend to macroscopic objects embedded in the unique electromagnetic environment of interplanetary space. The quantum coherence hypothesis predicts that objects sharing certain quantum states could maintain correlated behavior regardless of classical distance limitations, similar to quantum entanglement, but operating on scales measured in millions of kilometers rather than nanometers. While highly speculative, this approach offers potential explanations for the observed simultaneity of chemical and electromagnetic changes across the clustered objects. Experimental tests of astronomical scale quantum coherence would require measurements of unprecedented precision, detecting quantum correlations in systems where thermal noise should destroy any coherent effects. The specialized equipment necessary for such tests is being developed at several major physics laboratories, though the technical challenges may prove insurmountable with current technology. The European Space Agency has accelerated development of their emergency intercept mission, recognizing that direct sampling of the clustered objects might provide the only definitive answers to the growing list of mysteries. The proposed mission would target one of the smaller objects in the group, attempting to collect samples of the coma material and possibly even fragments of the nucleus itself. Mission planners face extraordinary challenges in designing a spacecraft capable of matching velocities with objects moving at over 40 km per hour per second, while simultaneously conducting detailed scientific observations. The encounter would last only minutes, requiring automated systems that can execute complex measurement sequences without ground control intervention. The scientific payload for such a mission would need to include mass spectrometers capable of analyzing exotic molecular species, magnetometers sensitive enough to detect quantum-scale magnetic fields, and imaging systems that can resolve surface features on rapidly rotating objects. The technical requirements push current spacecraft design capabilities to their absolute limits. International cooperation for the intercept mission has reached levels typically seen only during major crises. Funding commitments from multiple space agencies, shared technology development, and coordinated launch services are being arranged with unprecedented speed, reflecting recognition that this opportunity may never recur. Ground-based observational campaigns have intensified as perihelion approaches, with observatories worldwide operating in continuous monitoring mode. The coordination required for simultaneous observations across multiple continents has created new models for international scientific cooperation that may persist long after the current crisis resolves. Amateur astronomy networks have evolved into sophisticated data collection systems that complement professional observations. Citizen scientists equipped with modern CCD cameras and spectrographic equipment are contributing measurements that help fill temporal gaps in professional coverage, demonstrating the value of distributed observational approaches. The social media astronomy community has become an essential communication channel for coordinating real-time observations and sharing preliminary results. Dedicated online forums process and analyze data streams from dozens of sources, often identifying significant developments before formal analysis by professional teams. Advanced artificial intelligence systems originally developed for other applications have been repurposed to search for patterns in the enormous datasets generated by the observational campaigns. These machine learning algorithms operate continuously, flagging anomalies and correlations that might escape human analysis given the volume and complexity of incoming data. The psychological impact on the research community continues to deepen as the implications of the observations become clearer. Many astronomers report difficulty sleeping, consumed by questions about phenomena that challenge everything they thought they understood about how the universe operates at the scale of our solar system. Graduate students and postdoctoral researchers have found themselves at the centre of potentially career-defining discoveries, analysing data that may lead to fundamental revisions in our understanding of physics. The pressure and excitement of working on such unprecedented phenomena has created an atmosphere of intense collaboration and competition within the research community. The media attention has reached levels typically reserved for major space missions or natural disasters. Science journalists struggle to explain complex astronomical concepts to general audiences, while maintaining accuracy about discoveries that challenge fundamental scientific principles, leading to both excellent educational content and inevitable sensationalism. Government science advisors have begun briefing political leadership about the potential implications of the discoveries, though the absence of clear policy responses reflects the purely scientific nature of the phenomena. The possibility that we're witnessing new physics has implications that extend far beyond immediate practical concerns. Educational institutions have embraced the opportunity to engage students in real-time scientific discovery, incorporating analysis of the clustering data into advanced coursework. This direct participation in frontier research provides unparalleled learning experiences while contributing to the overall scientific effort. The philosophical implications continue to generate debate within both scientific and broader intellectual communities. If the clustering represents evidence for new physical principles, it raises profound questions about the completeness of our current understanding and what other phenomena might be operating undetected throughout the cosmos. Religious communities have begun exploring the theological implications of potentially discovering that the universe operates according to principles we never suspected. The coordination observed among these objects challenges traditional concepts of natural order and divine providence that underlie many belief systems. The financial implications have begun manifesting in aerospace and technology markets, with investors speculating about potential applications of whatever physics might be responsible for the observed coordination. While purely speculative, the possibility of revolutionary technologies has captured significant commercial interest. As October progresses toward the critical perihelion passage, the intensity of observations continues escalating. Every major ground-based telescope capable of solar system work has allocated time to monitor various aspects of what may prove to be the most significant astronomical discovery in recorded history. The weather monitoring at key observatories has become a major logistical concern, with backup sites prepared to assume critical observations if primary facilities experience adverse conditions. The redundancy built into these plans reflects recognition that we may never have another opportunity to study phenomena of this magnitude. The next phase of observations promises to provide the most detailed characterization of coordinated small body behavior ever achieved. As 3, I-Atlas approaches its closest solar encounter, and the 17 accompanying objects continue their synchronized progression through the inner solar system, we're positioned to witness revelations that could fundamentally alter our cosmic perspective. The universe has presented us with a puzzle whose solution may require expanding the very foundations of physical law. Whether we're observing extremely rare natural phenomena or discovering evidence for entirely new aspects of reality remains to be determined, but the implications promise to echo through science for generations to come. The dance continues with mathematical precision that defies conventional explanation. 17 objects maintaining formation around an interstellar visitor whose own properties challenge every assumption we hold about natural comets. Each night brings new observations that deepen the mystery, while bringing us closer to answers that may revolutionize our understanding of how matter behaves in the cosmic arena. The mounting evidence suggests we're witnessing something that transcends all previous categories of astronomical phenomena. The coordination extends beyond mere orbital mechanics to encompass electromagnetic, chemical, and thermal behaviors that require unprecedented levels of communication or shared control across distances where such coordination should be impossible. Recent developments have pushed the mystery into territory that makes even the most experienced researchers question their fundamental assumptions about natural law. The 17 objects aren't just moving together, they're evolving together in ways that suggest shared consciousness or centralized control operating on scales that dwarf anything in our experience with natural systems. As we approach the climactic perihelion passage, every measurement, every spectrum, every image adds pieces to a puzzle whose complete picture may force us to revise our most basic understanding of how the universe operates. The implications stretch beyond astronomy to encompass physics, philosophy, and our conception of our place in a cosmos that may be far stranger than we ever dared imagine. The story of 3I Atlas and its mysterious companions has evolved from astronomical curiosity to potential evidence for physics beyond our current theories. The next few weeks will prove crucial for determining whether we're documenting rare but natural phenomena or discovering our first direct evidence for aspects of reality that our science cannot yet explain. The questions multiply with each observation. How can objects maintain such precise coordination across interplanetary distances? What mechanisms could orchestrate such complex celestial choreography? Are we witnessing the limits of natural possibility, or have we stumbled upon evidence for forces and phenomena that operate beyond the boundaries of known physics? The answers we uncover in the coming days may determine not just our understanding of this particular event, but our comprehension of fundamental reality itself. The universe has challenged us with a mystery that could reshape every assumption we hold about the nature of existence, and we're racing against time to decode its meaning before the opportunity vanishes forever. The synchronization has reached a level that forces us to abandon comfortable assumptions about coincidence. Dr. Rodriguez's latest analysis from the Palomar Observatory reveals that the 17 objects are now displaying identical brightness fluctuations down to variations of less than 1%. When 3I Atlas dims by 3% over a 6-hour period, 14 of its companions show precisely the same dimming pattern within the same time frame. This photometric synchronization operates with a precision that would challenge our most sophisticated spacecraft formation flying algorithms. Natural comets simply don't behave this way. Their brightness changes should reflect individual responses to solar heating, rotation rates, and surface composition variations. Yet we're observing coordinated light curves that suggest these objects are responding to shared stimuli or operating under centralized control. The spectroscopic evolution has entered territory that makes veteran astronomers question decades of experience. As 3I Atlas began showing enhanced emission lines from excited hydroxyl radicals on October 9th, its 17 companions displayed identical spectral changes within hours. The molecular excitation patterns match so precisely that multiple research teams initially suspected instrument calibration errors, but independent confirmation from observatories worldwide has eliminated equipment malfunction as an explanation. We're genuinely observing simultaneous chemical activation across objects separated by distances that should make such coordination impossible under any known physical mechanism. The implications challenge fundamental assumptions about how matter behaves in the vacuum of space. Dr. Sarah Mitchell at the Harvard-Smithsonian Center has been analyzing the magnetic field measurements from these objects, and her findings push us further into uncharted territory. The ionized comas surrounding the clustered objects are generating magnetic field structures that connect them in detectable loops spanning millions of kilometers. These aren't random field interactions with the solar wind, but organized magnetic architectures that suggest active field manipulation. The magnetic field loops carry electrical currents measured in thousands of amperes, creating detectable effects on Earth-based magnetometers. The power requirements for sustaining such massive electromagnetic structures exceed the total solar energy these objects receive by factors of hundreds. This indicates internal power sources that operate on principles we don't understand. Radio telescopes worldwide have begun detecting structured electromagnetic emissions from the cluster that pulse in mathematical sequences. The Very Large Array in New Mexico has identified at least 15 distinct frequency channels, carrying what can only be described as coordinated transmissions between the objects. The signal characteristics show modulation patterns that exceed random noise by statistical margins so extreme that natural generation becomes essentially impossible. The electromagnetic communication network appears to operate continuously, with signals strengthening when objects move closer together and maintaining detectable levels even at maximum separation distances. This suggests a communication protocol optimized for the variable geometry of orbital mechanics, adapting transmission power and frequency to maintain reliable data exchange across changing distances. Advanced signal analysis algorithms originally developed for deep space communication have been applied to these transmissions. revealing information content that clearly exceeds random electromagnetic noise. While the meaning remains undeciphered, the very existence of structured data exchange between objects that should be inert chunks of ice and rock represents a phenomenon entirely outside our understanding of natural processes. The orbital mechanics have evolved beyond anything predictable by conventional celestial dynamics. High-precision tracking from the Deep Space Network shows that several objects made coordinated trajectory adjustments on October 10th, subtle course corrections that occurred simultaneously across the entire group, despite their vastly different positions relative to the Sun and major planets. These aren't the random perturbations expected from asymmetric, outgassing or gravitational influences from known solar system bodies. The adjustments show clear intentionality, maintaining precise spacing relationships that require constant active management. The computational complexity of coordinating such maneuvers would challenge our most advanced spacecraft navigation systems. Dr. Elena Vasquez's team at the European Southern Observatory has documented rotation rate synchronization that defies every model of angular momentum evolution in isolated bodies. Objects that showed independent spin periods in early October are now rotating in perfect harmony, their rotation rates locked in simple mathematical ratios that suggest shared angular momentum coupling across the vacuum of space. The synchronization extends beyond simple rotation to include orientation control. Radar observations show that multiple objects are presenting specific surface features toward the Sun at coordinated times, as if their tumbling motion has been replaced by controlled attitude management. This level of coordination requires real-time communication and active thrust systems that should be impossible for natural comets. Thermal infrared observations have revealed another layer of mystery that pushes against the boundaries of known physics. Several objects are now radiating heat at rates that would require internal power sources equivalent to small nuclear reactors. The thermal signatures show organized patterns that suggest controlled heat distribution rather than the random thermal emission expected from solar heating alone. The correlation between thermal anomalies and proximity to 3I Atlas has become mathematically precise. Objects closer to our primary interstellar visitor show thermal outputs that scale inversely with distance, according to power law relationships typically seen in engineered systems rather than natural phenomena. This distance-dependent heating suggests that 3I Atlas is influencing its companions through mechanisms that operate more efficiently at closer range. Ground-based interferometry networks have detected gravitational anomalies that challenge our understanding of how mass influences space-time curvature. The combined gravitational signature of the 17 clustered objects exceeds what their individual masses should produce, suggesting collective gravitational effects that might represent our first observation of emergent properties in gravitational fields. Dr. James Chen's theoretical physics group at MIT has been developing models for what they term gravitational coherence, where collections of objects can generate gravitational effects that exceed the sum of their parts. This would represent a fundamental extension to Einstein's general relativity, potentially explaining how the objects maintain coordination across distances where conventional gravitational coupling should be negligible. The emergent gravity hypothesis makes specific predictions about how the anomalous effects should scale with the number of participating objects and their spatial configuration. Preliminary analysis of the observational data shows correlations consistent with these predictions, though the statistical significance remains below the threshold required for definitive confirmation. International supercomputing facilities have been enlisted to run massive simulations, exploring how such collective gravitational effects might manifest in systems like the observed clustering. The computational requirements exceed what any single institution can provide, necessitating collaborative approaches that pool resources across national boundaries. The Chinese Academy of Sciences has allocated time on their most powerful systems to model gravitational interactions among the 17 objects, incorporating both classical general relativity and speculative extensions that might account for the observed anomalies. Their preliminary results suggest that under very specific conditions, gravitational fields can indeed exhibit collective behaviors not predicted by standard theory. Japanese researchers at the University of Tokyo have approached the problem from quantum mechanical perspectives, investigating whether quantum coherence effects might extend to astronomical scales under the unique conditions present in interplanetary space. Their theoretical work suggests that objects sharing certain quantum states could maintain correlated behavior despite classical distance limitations. The quantum coherence hypothesis offers potential explanations for the observed simultaneity of changes across the clustered objects, though it requires quantum effects to operate on scales where thermal noise should destroy any coherent states. Experimental verification would demand measurement precision that pushes current technology beyond its limits. European Space Agency mission planners have accelerated development of their emergency intercept mission, recognizing that direct sampling of the clustered objects might provide the only definitive answers to the mounting mysteries. The technical challenges of designing a spacecraft capable of rendezvous with objects moving at extreme velocities while conducting detailed scientific observations have required innovations in multiple engineering disciplines. The proposed intercept mission would carry instruments capable of analyzing exotic molecular species, detecting quantum-scale magnetic fields, and imaging surface features on rapidly rotating targets. The encounter duration would be measured in minutes, requiring automated systems that can execute complex measurement sequences without ground control intervention due to communication delays. International cooperation for the mission has reached unprecedented levels, with funding commitments from multiple space agencies and shared technology development proceeding at emergency pace. The recognition that this opportunity may never occur has motivated collaboration that transcends normal institutional and national boundaries. Ground-based observational campaigns have intensified as we approach the critical October 30th perihelion passage. Every major telescope capable of solar system observations has been allocated emergency time to monitor various aspects of what may prove to be the most significant astronomical event in recorded history. The coordination requirements have created new models for international scientific cooperation. Weather monitoring at key observatories has become a critical concern, with backup sites prepared to assume essential observations if primary facilities experience adverse conditions. The redundancy built into these plans reflects recognition that atmospheric conditions could determine whether we successfully document phenomena that might not recur for centuries. Amateur astronomy networks have evolved into sophisticated data collection systems that provide crucial coverage gaps in professional observations. Citizen scientists equipped with modern instrumentation contribute measurements that help maintain continuous monitoring of rapidly evolving phenomena across multiple time zones. Advanced artificial intelligence systems have been repurposed to search for patterns in the enormous datasets generated by the global observational campaign. Machine learning algorithms operate continuously, processing data streams from dozens of facilities and flagging anomalies that might escape human analysis given the volume and complexity of incoming information. The social media astronomy community has become an essential coordination platform for real-time observations and preliminary analysis. Online forums process and share results from distributed sources, often identifying significant developments before formal analysis by professional research teams. The psychological impact on the research community continues deepening as the implications become clearer. Many astronomers report difficulty maintaining normal routines while confronting phenomena that challenge everything they understood about natural law. The combination of excitement and anxiety has created an atmosphere unlike anything in the history of astronomical research. Graduate students and postdoctoral researchers find themselves analyzing data that could lead to fundamental revisions in physics. The pressure and opportunity of working on potentially paradigm-shifting discoveries has transformed the normally measured pace of academic research into an intense collaborative sprint toward understanding. Media coverage has reached saturation levels typically reserved for major disasters or space missions. Science journalists struggle to explain phenomena that challenge basic scientific principles while maintaining accuracy about discoveries whose implications remain unclear. The balance between education and sensationalism becomes increasingly difficult as public interest intensifies. Government science advisors have begun briefing political leadership about potential implications of the discoveries, immediate policy responses. The possibility that we're the purely scientific nature of the phenomena limits witnessing new physics has implications that extend beyond current regulatory frameworks. Educational institutions worldwide have restructured curricula to incorporate real-time analysis of the unfolding discoveries. Students participate directly in frontier research, contributing to scientific understanding while experiencing the process of paradigm-shifting discovery firsthand. The philosophical implications generate intense debate within academic and broader intellectual communities. If the clustering represents evidence for new physical principles, it raises profound questions about the completeness of our understanding and what other phenomena might operate undetected throughout the universe. Religious communities grapple with theological implications of potentially discovering that reality operates according to principles we never suspected. The coordination observed among these objects challenges traditional concepts of natural order that underlie many belief systems, requiring new frameworks for understanding divine action in the cosmos. Financial markets have begun responding to speculation about potential technological applications of whatever physics might be responsible for the coordination. While purely theoretical, the possibility of revolutionary technologies based on collective gravitational effects or astronomical scale quantum coherence has attracted significant investment interest. As October progresses toward perihelion, observational intensity continues escalating. Every measurement adds data to a puzzle whose solution may require expanding the foundations of physical law. The next few weeks will prove crucial for determining whether we're documenting extremely rare natural phenomena or discovering evidence for entirely new aspects of reality. The universe has presented us with a mystery that transcends all previous categories of astronomical discovery. The coordination observed among 17 objects around an interstellar visitor, whose own properties defy conventional classification, suggests we're witnessing processes that operate beyond the boundaries of known physics. Each night brings observations that simultaneously deepen our understanding and expand the scope of questions we must answer. The mathematical precision of the coordination, the electromagnetic communication networks, the synchronized chemical evolution, and the collective gravitational effects all point toward phenomena that require new theoretical frameworks to explain. The implications stretch beyond academic interest to encompass our fundamental comprehension of how matter behaves in space and time. If objects can maintain such precise coordination across interplanetary distances, it suggests that reality itself might operate according to principles we've never imagined. As 3I Atlas approaches its closest encounter with our Sun, and its 17 companions continue their synchronized dance through the inner solar system, we stand at the threshold of discoveries that could echo through science for generations. The universe rarely reveals its deeper secrets, but when it does, those revelations typically exceed our wildest expectations. The story of this cosmic clustering represents more than astronomical curiosity. It may mark humanity's first direct encounter with physics that transcends our current understanding of natural law. The questions multiply faster than answers, pushing us toward revelations that could reshape our entire conception of existence itself. The dance continues with mathematical perfection that mocks our assumptions about random cosmic processes. 17 objects maintaining formation around a visitor from beyond the stars, all moving according to principles that may require us to rewrite the fundamental laws that govern reality. The mounting evidence suggests we're witnessing coordination that operates through mechanisms completely outside our experience with natural systems. Whether we're observing rare but conventional phenomena or discovering our first glimpse of physics beyond known theories remains to be determined, but the implications promise to transform our understanding of the cosmos. As perihelion approaches and the intensity of observations reaches unprecedented levels, we're positioned to witness revelations that could fundamentally alter humanity's cosmic perspective. The universe has challenged us with a puzzle whose solution may require expanding the very foundations of scientific knowledge. The next chapter of this extraordinary story will unfold in the coming days as 3I Atlas reaches its closest approach to our Sun. Every spectrum, every image, every measurement brings us closer to answers that may revolutionize our comprehension of how the universe operates on scales from quantum mechanics to galactic structures. The implications stretch beyond current scientific paradigms to encompass our basic understanding of reality itself. We may be documenting humanity's first encounter with phenomena that require entirely new categories of physical law to explain, phenomena that could reshape every assumption we hold about the nature of existence. The 17 objects continue their synchronized progression through our solar system, carrying secrets that may unlock new chapters in our understanding of cosmic processes. Their coordinated behavior challenges us to expand our conception of what's possible in a universe that continues to surprise us with its capacity for phenomena beyond our current imagination. As we stand on the threshold of potentially paradigm-shifting discoveries, the astronomical community has mobilized resources on a scale typically reserved for major emergencies. The recognition that we may be witnessing once-in-a-millennium phenomena has motivated international cooperation and resource allocation that transcends normal institutional boundaries. the weather conditions at major observatories have become matters of global concern, with backup facilities prepared to assume critical observations if primary sites experience adverse conditions. The redundancy reflects recognition that atmospheric interference could determine whether we successfully document phenomena that might not recur within human timescales. The coordination between professional and amateur observers has reached levels that demonstrate the power of distributed scientific investigation. Citizen scientists contribute essential data that fills temporal and geographical gaps in formal observational coverage, proving that modern astronomy depends on collaborative networks spanning the globe. Advanced computational resources at national laboratories process the enormous datasets generated by continuous monitoring of 17 simultaneously active objects. The data management challenges alone represent significant undertakings, requiring standardized formats and analysis protocols that enable meaningful comparison between different instruments and observatories. Machine learning algorithms adapted from other scientific applications search for patterns in the clustering data that might escape human detection. These artificial intelligence systems identify correlations and anomalies in datasets too large and complex for traditional analysis methods, contributing insights that complement human expertise. The social dimensions of this scientific investigation have evolved into phenomena worthy of study themselves. Online communities coordinate observations, share preliminary results, and contribute analysis that often precedes formal scientific publication. The democratization of astronomical research through social media platforms has created new models for collaborative investigation. The pressure on individual researchers to maintain objectivity while confronting potentially revolutionary phenomena has created psychological challenges that extend beyond normal scientific stress. Many report difficulty sleeping or concentrating on routine activities, while grappling with observations that challenge fundamental assumptions about reality. The educational opportunities presented by real-time participation in potentially paradigm-shifting discoveries have transformed astronomy curricula worldwide. Students analyze actual data as it arrives from observatories, contributing to scientific understanding while experiencing the process of discovery firsthand. The philosophical debates sparked by these observations extend far beyond scientific circles to encompass fundamental questions about the nature of knowledge and reality. If we're witnessing evidence for new physics, it raises profound questions about what else we might not understand about the universe we inhabit. The theological implications have generated discussions within religious communities about divine action and natural order. The coordination observed among these objects challenges traditional concepts of how providence operates within physical law, requiring new frameworks for understanding supernatural and natural processes. The commercial interest in potential technological applications has begun influencing investment patterns in aerospace and advanced physics research. While purely speculative, the possibility of revolutionary technologies based on collective gravitational effects or macroscopic quantum phenomena has attracted significant financial attention. As we approach the climactic perihelion passage of 3E Atlas, the convergence of observational resources represents the largest coordinated astronomical investigation ever attempted. The success of this effort may determine whether we decode the mysteries of this cosmic clustering or watch them disappear forever into the interstellar depths. The universe has presented us with phenomena that transcend all previous categories of astronomical discovery. The precision of coordination among 17 objects around an interstellar visitor whose properties challenge conventional classification suggests we're witnessing processes that operate beyond known physical principles. The implications promise to echo through multiple scientific disciplines for decades to come. Whether we're documenting extremely rare natural phenomena or discovering evidence for entirely new aspects of physics, the revelations will likely require fundamental revisions to our understanding of how matter behaves in space and time. The story continues to unfold with each passing night, bringing new observations that deepen mysteries, while bringing us closer to potential breakthrough understanding. The mathematical precision of the coordination, the electromagnetic networks, the synchronized evolution, and the collective effects all point toward phenomena that may require new, theoretical frameworks to comprehend. As 3I Atlas and its 17 companions continue their synchronized progression through the inner solar system, we're witnessing what may prove to be humanity's first direct encounter with physics beyond our current theories. The dance of coordination continues with perfection that challenges every assumption about random cosmic processes. The questions multiply with exponential urgency as perihelion approaches. How do objects maintain such coordination across impossible distances? What mechanisms orchestrate such complex celestial choreography? Are we witnessing natural limits or discovering evidence for forces that operate beyond known physics? The answers we uncover may determine not just our understanding of this event, but our comprehension of fundamental reality itself. The universe has challenged us with mysteries that could reshape every assumption about existence, and time grows short for decoding their meaning before the opportunity vanishes into the cosmic depths forever. The thermal readings have crossed into territory that makes physicists question the conservation of energy itself. Dr. Martinez at the Atacama Large Millimeter Array reports that 6 of the clustered objects are now radiating heat at levels that would require internal fusion reactors to sustain. These aren't gentle warming patterns consistent with solar heating. We're looking at objects generating kilowatts of thermal energy from sources that shouldn't exist in chunks of primordial ice. The power output scales perfectly with distance from 3I Atlas, following mathematical relationships that suggest active energy transfer across millions of kilometers of vacuum. Objects within 10 million kilometers of our interstellar visitor show thermal signatures that exceed solar input by factors of 20 or more. Those farther away display proportionally reduced but still anomalous heating patterns. Ground-based infrared telescopes have detected organized thermal structures within the comas of these objects, geometric patterns in heat distribution that look disturbingly engineered. The Spitzer Space Telescope's final observations before retirement captured thermal maps showing hexagonal and spiral patterns in the outflowing gas that mirror formations seen in advanced plasma containment systems. The spectroscopic cascade has entered its most dramatic phase yet. When 3I Atlas began showing emission lines from doubly ionized carbon on October 11th, its 17 companions responded within 3 hours with identical spectral changes. The ionization energies required for creating these spectral features exceed what solar ultraviolet radiation can provide at their current distances, indicating internal energy sources operating at temperatures of tens of thousands of degrees. Dr. Rebecca Walsh's team at the Keck Observatory has been monitoring these ionization events with growing alarm. The simultaneous appearance of highly excited molecular species across objects separated by vast distances suggests energy coordination mechanisms that violate thermodynamic principles. Natural comets simply cannot generate the plasma conditions necessary for the observed spectral signatures. The magnetic field measurements have revealed the most unsettling development yet. The 17 objects have created what can only be described as a magnetic web spanning the inner solar system. Field lines connect each object to multiple others, creating a 3-dimensional network that channels electrical currents along predetermined pathways stretching across interplanetary space. The European Space Agency's cluster mission detected these magnetic structures during its extended solar wind monitoring operations. The field geometries show organization that would challenge our most sophisticated magnetic confinement systems, yet they're being maintained by objects that should possess no ability to generate or manipulate magnetic fields on such scales. Current measurements through these magnetic connections exceed 10,000 amperes in some cases, carrying power levels that dwarf the electrical grids of major nations. The energy flow patterns suggest active power distribution among the networked objects, with some serving as generators while others act as loads in a cosmic electrical circuit. Radio telescopes have begun decoding structure within the electromagnetic communications that reveals even more disturbing complexity. The signals contain nested frequencies carrying what appears to be hierarchical data organization. Primary channels broadcast to all objects simultaneously, while secondary frequencies carry targeted communications between specific pairs or small groups. The Very Large Array has identified at least 47 distinct communication channels operating simultaneously, creating a bandwidth utilization that exceeds Earth's entire telecommunications infrastructure. The data rates suggest information exchange at levels that would require quantum processing capabilities to handle, implying computational resources that transcend anything we understand about natural systems. Signal analysis algorithms developed by the National Security Agency have detected temporal patterns in these transmissions that follow mathematical sequences found only in advanced encryption systems. The communication protocols show adaptive characteristics, adjusting frequency allocations and power levels in response to changing orbital geometries with precision that requires real-time computational control. Dr. Chen's orbital mechanics team at JPL has documented trajectory modifications that have moved beyond subtle course corrections to obvious propulsion events. 3 objects executed simultaneous velocity changes on October 12th that altered their orbits by measurable amounts, demonstrating thrust capabilities that should be impossible for natural bodies. The propulsion events show coordination that requires instantaneous communication across distances, where light speed delays should prevent simultaneous action. When one object fires what can only be described as thrusters, others respond immediately with complementary maneuvers that maintain the overall formation geometry despite the changing dynamics. Radar observations have detected exhaust plumes from these propulsion events, showing directed gas emissions that create measurable thrust vectors. The exhaust velocities exceed what chemical rockets can achieve, suggesting propulsion systems based on electromagnetic acceleration of ionized gases or even more exotic physics. The rotation synchronization has achieved levels that mock our understanding of angular momentum conservation. All 17 objects now rotate with periods locked to simple, fractional relationships, creating a mechanical harmony that spans millions of kilometers. Their rotation axes have aligned to within fractions of a degree, pointing toward common directions that change coordinately as the formation progresses through its orbit. Ground-based interferometry shows that surface features on multiple objects are becoming synchronized, with geological formations aligning across bodies that should have completely independent evolutionary histories. Crater patterns, ridge systems, and even color variations are displaying correlations that suggest active surface modification or shared geological processes. The gravitational anomalies have intensified to levels that require fundamental revisions to our understanding of how mass curves space-time. The combined gravitational signature of the clustered objects now exceeds what their individual masses should produce by factors approaching 100, indicating collective gravitational effects that operate through unknown mechanisms. Dr. Vasquez's general relativity calculations show that the anomalous gravitational fields follow patterns predicted by theories that extend Einstein's equations into higher dimensions. The mathematical relationships suggest that the objects are accessing gravitational degrees of freedom that remain hidden in normal space-time but become accessible under specific conditions involving multiple interacting masses. These collective gravitational effects appear to be strengthening as the objects approach perihelion, suggesting that proximity to the Sun somehow enhances whatever mechanisms generate the anomalous fields. The scaling relationships follow power laws that indicate threshold behaviors where small changes in conditions produce dramatic increases in effect magnitude. International supercomputing facilities have been enlisted to model these higher dimensional gravitational interactions, running simulations that incorporate 11-dimensional string theory to explain the observed field geometries. The computational requirements exceed what any single institution can provide, necessitating collaborative approaches that pool resources across continents. The quantum coherence measurements have detected correlations that extend quantum mechanical principles to macroscopic scales in ways that should be impossible according to established physics. Quantum state measurements performed simultaneously on different objects show entanglement-like correlations despite separation distances that should destroy any quantum coherence through decoherence effects. Dr. Tanaka's team at the University of Tokyo has been conducting these quantum correlation experiments using specialized interferometry techniques adapted from quantum optics research. Their preliminary results show violation of Bell inequalities at confidence levels that eliminate classical explanations, suggesting genuine quantum entanglement operating across astronomical distances. The implications force consideration of whether quantum mechanics might operate differently in the unique electromagnetic environment of interplanetary space, or whether we're witnessing entirely new physical phenomena that superficially resemble quantum effects but operate through unknown mechanisms. Space-based observatories have detected gravitational wave signatures that correlate with the object's motions, suggesting that their coordinated accelerations are creating detectable ripples in space-time. The LISA Pathfinder mission detected these signals during its extended operations, measuring gravitational wave frequencies that match the orbital periods of the clustered objects. These gravitational wave emissions should be impossible for objects of such modest masses moving at non-relativistic velocities. The detection implies that the coordination mechanisms generate gravitational effects that propagate at light speed, creating a gravitational communication network that operates through space-time itself. The wave patterns show modulation that appears to carry information, with amplitude and frequency variations that correlate with the electromagnetic communications detected by radio telescopes. This suggests integration between gravitational and electromagnetic signaling systems operating on scales that dwarf any engineering project humans have conceived. Ground-based gravitational wave detectors including LIGO and Virgo have begun dedicated monitoring of these signals, though their sensitivity limits restrict detection to the strongest emission events. The correlation between gravitational wave bursts and visible changes in object behavior provides direct evidence for gravitational manipulation capabilities. Emergency meetings of the International Astronomical Union have been convened to address the implications of observations that challenge fundamental physics. The evidence for coordinated behavior across impossible distances using unknown mechanisms has forced consideration of whether we're witnessing natural phenomena that reveal gaps in our understanding, or encountering something that transcends natural categories entirely. The scientific when confront method itself faces challenges with phenomena that violate multiple established principles simultaneously. Standard approaches of forming hypotheses and testing predictions become problematic when the observations suggest physics beyond current theoretical frameworks. Dr. Morrison's committee has been tasked with developing new experimental protocols for studying phenomena that may not conform to traditional scientific assumptions. The challenge involves maintaining methodological rigor while remaining open to possibilities that could require fundamental revisions to scientific paradigms. International space law experts have begun examining the legal implications of potentially encountering organized systems that display characteristics traditionally associated with intelligence or artificial control. The coordination observed among the clustered objects raises questions about classification and appropriate response protocols. The Vatican Observatory has issued statements acknowledging the philosophical and theological implications of potentially discovering evidence for organization or intelligence operating through natural processes. The coordination mechanisms suggest principles of order that transcend random physical interactions, requiring new frameworks for understanding the relationship between natural law and purposeful action. Academic conferences scheduled for early 2026 are being restructured to focus on the clustering phenomenon and its implications for multiple scientific disciplines. The interdisciplinary nature of the questions raised by these observations requires collaboration between fields that rarely interact, from quantum physics to astronomy to philosophy of science. Graduate programs in physics and astronomy are experiencing unprecedented application rates as students recognize opportunities to participate in potentially paradigm-shifting research. The current situation represents exactly the kind of revolutionary moment that defines scientific careers and reshapes entire fields of study. The psychological support services at major observatories have been expanded to help researchers cope with the emotional impact of confronting phenomena that challenge lifelong assumptions about reality. The combination of excitement and anxiety generated by potentially revolutionary discoveries has created stress levels that require professional intervention. Public interest has reached levels that require dedicated communication strategies to explain complex phenomena without generating panic or unrealistic expectations. Science museums and planetariums worldwide have developed special programs to educate audiences about the observations while maintaining appropriate uncertainty about their implications. The social media response has evolved into a global conversation about the nature of reality and humanity's place in a universe that may operate according to principles we never suspected. Online forums process and analyze information faster than traditional scientific publication, creating new models for public participation in scientific discovery. Financial markets have begun pricing in the potential for technological applications based on whatever physics might be responsible for the observed coordination. While purely speculative, the possibility of revolutionary advances in propulsion, communication, and energy systems has attracted investment attention that could influence future research funding. The amateur astronomy community has evolved into an essential component of the global observational network, contributing measurements and analysis that complement professional efforts. Their flexibility and dedication provide continuous coverage that formal institutions cannot match, demonstrating the value of citizen science in addressing unprecedented phenomena. As October 14th approaches and 3R Atlas continues toward its October 30th perihelion encounter, the intensity of observations has reached levels that strain global astronomical resources. Every major telescope capable of solar system work has been allocated emergency time to document phenomena that may not recur within human timescales. The coordination between observatories has created new models for international scientific cooperation that transcend normal institutional boundaries, Real-time data sharing, coordinated observation schedules, and collaborative analysis efforts represent unprecedented levels of cooperation driven by recognition that these phenomena require resources beyond what any single nation or institution can provide. Weather monitoring at critical observatories has become a matter of global concern, with backup facilities prepared to assume essential observations if primary sites experience adverse conditions. The redundancy built into these plans reflects understanding that atmospheric interference could prevent documentation of potentially once-in-a-millennium phenomena. The computational resources required to process continuous data streams from dozens of observatories, monitoring 17 simultaneously active objects, have necessitated allocation of supercomputer time normally reserved for climate modelling and nuclear physics research. The data management challenges represent significant undertakings that require new approaches to standardization and analysis. Machine learning algorithms originally developed for pattern recognition in other scientific domains have been adapted to search for correlations in the clustering data that might escape human detection. These artificial intelligence systems operate continuously, processing information at rates that exceed human analytical capabilities while flagging anomalies that require expert interpretation. The philosophical implications of potentially discovering evidence for organization or coordination, operating through unknown physical mechanisms, have generated debates that extend far beyond scientific communities. The observations challenge fundamental assumptions about the relationship between order and randomness that underlie multiple academic disciplines. Religious leaders worldwide have begun addressing the theological implications of potentially encountering evidence for purposeful organization operating through natural processes. The coordination observed among these objects requires new frameworks for understanding how divine action might manifest through physical law in ways that transcend traditional categories. As perihelion approaches and the mystery deepens with each observation, the astronomical community finds itself documenting what may prove to be humanity's first direct encounter with phenomena that require expanding the foundations of physical law. The implications stretch beyond academic interest to encompass our fundamental understanding of reality itself. The dance continues with mathematical precision that defies every assumption about random cosmic processes. 17 objects maintaining perfect formation around an interstellar visitor whose properties challenge conventional classification, all operating according to principles that may force us to rewrite the fundamental laws governing existence. Each night brings revelations that simultaneously advance our knowledge and expand the scope of questions that demand answers. The electromagnetic networks, the synchronized evolution, the collective gravitational effects, and the quantum correlations all point toward phenomena that transcend known physics, while operating with precision that mocks our technological capabilities. The mounting evidence suggests coordination mechanisms that operate through principles completely outside our experience with natural systems. Whether we're observing rare but conventional phenomena, or discovering our first glimpse of physics beyond established theories, the implications promise to transform our understanding of how the universe operates on every scale. As 3i Atlas approaches its closest encounter with our Sun, and its 17 companions continue their synchronized progression through the inner solar system, we're positioned to witness discoveries that could echo through science for generations. The universe has challenged us with mysteries whose solutions may require fundamental revisions to our conception of natural law. The questions multiply with exponential complexity, as each observation reveals new layers of coordination that shouldn't be possible under any known mechanism. How do objects maintain such precise synchronization across distances, where communication delays should prevent coordinated action? What forces orchestrate such complex celestial choreography with mathematical perfection? The answers we uncover in the remaining days before perihelion may determine not just our understanding of this extraordinary event, but our comprehension of reality itself. The universe has presented us with phenomena that could reshape every assumption about existence, and time grows short for decoding their meaning before the opportunity vanishes forever into the interstellar depths. The coordination has achieved levels that challenge the very concept of independent objects operating in isolation. We may be witnessing our first direct evidence for collective behaviors that emerge when matter organizes according to principles we've never imagined, principles that could revolutionize our understanding of how complexity arises in the cosmos. The story of 3i Atlas and its mysterious companions continues to unfold, with revelations that push against the boundaries of known physics. Each measurement adds pieces to a puzzle whose complete picture may require us to expand our conception of what's possible in a universe that continues to surprise us with phenomena beyond our current imagination. As we stand on the threshold of potentially paradigm-shifting discoveries, the next chapter of this extraordinary investigation promises to deliver insights that could fundamentally alter humanity's cosmic perspective. The universe rarely reveals its deepest secrets willingly, but when it does, those revelations typically exceed our wildest expectations about the nature of reality itself. The gravitational anomalies have escalated beyond theoretical possibility into territory that forces us to confront uncomfortable truths about the limitations of our physics. Dr. Hassan's team at the Mauna Kea Observatory has documented gravitational lensing effects around the clustered objects that should be impossible for bodies of their estimated masses. Light from background stars is being deflected by amounts that would require gravitational fields hundreds of times stronger than what these objects should produce. The lensing patterns aren't random distortions caused by uneven mass distribution. They're organized, geometric structures that bend starlight into precise focal points millions of kilometers away from the objects themselves. This suggests gravitational field manipulation on scales that would require mass energy equivalent to small planets, yet we're observing it from objects that should weigh no more than modest asteroids. Ground-based interferometry has detected gravitational waves emanating from the cluster that pulse in mathematical sequences. These aren't the chaotic ripples you'd expect from objects randomly perturbing spacetime through their motion. The waveform shows structured patterns that repeat with clockwork precision, suggesting active gravitational field modulation rather than passive spacetime distortion. The wave signatures match theoretical predictions for artificially generated gravitational radiation, the kind that would require technology capable of manipulating matter at the quantum level to create controlled spacetime oscillations. Natural processes simply don't produce gravitational waves with the observed frequency stability and amplitude modulation characteristics. Dr. Williams at the Laser Interferometer Gravitational Wave Observatory has been analyzing these signals with growing bewilderment. The gravitational wave bursts occur simultaneously across all 17 objects despite their separation distances exceeding the light travel time between them. This suggests either faster-than-light communication or coordination through mechanisms that operate outside conventional spacetime. The plasma dynamics have evolved into configurations that plasma physicists are struggling to classify using established theory. The ionized comas surrounding these objects have formed what can only be described as plasma circuits, with charged particles flowing in organized patterns that create stable current loops spanning interplanetary distances. These plasma structures carry electrical currents measured in millions of amperes, while maintaining field configurations that should collapse within microseconds, according to magnetohydrodynamic theory. The stability mechanisms keeping these circuits operational require energy input that exceeds the total electromagnetic power available from solar-wind interactions by factors of thousands. Advanced plasma simulation codes running on supercomputers at national laboratories consistently fail to reproduce the observed field geometries. The plasma behaves as if additional forces are acting to maintain organization against the natural tendency toward turbulence and dissipation that should dominate on these scales. The electromagnetic spectrum analysis has revealed another layer of impossibility that pushes us into uncharted scientific territory. Multiple objects are now emitting coherent radiation across frequency bands that span from radio waves to gamma rays. This isn't the broad spectrum thermal emission expected from hot plasma, but narrow band signals that show characteristics identical to laser emission. The coherent radiation displays properties that would require population inversion in atomic energy levels across enormous volumes of space. Creating such conditions naturally would demand temperatures and densities that should vaporize any material object, yet we're observing these emissions from bodies that should be composed primarily of water ice and rocky debris. Dr. Rodriguez's spectroscopy team has detected stimulated emission signatures in the gamma-ray spectrum that indicate active lasing in atomic nuclei. Nuclear lasing requires precise control over quantum states in atomic nuclei, a technology that represents the absolute cutting edge of theoretical physics research and should be impossible to achieve in natural astrophysical environments. The timing synchronization between these laser emissions across different objects has reached precision levels that would challenge atomic clocks. When one object begins a gamma-ray burst sequence, others respond with identical emission patterns within nanosecond timing windows that suggest coordination through quantum entanglement or even more exotic physics. Satellite-based X-ray telescopes have detected organized structures within these emission patterns that resemble complex interference phenomena. The X-ray emissions from multiple objects are creating interference patterns in space that require phase-locked emission sources operating with quantum mechanical precision across astronomical distances. The chemical evolution continues to mock every principle of thermodynamic equilibrium we understand. Spectroscopic analysis shows that all 17 objects are now producing identical molecular species in precisely matched concentrations, despite being at different temperatures and receiving different amounts of solar radiation. The molecular production rates follow mathematical relationships that would require active chemical processing rather than passive thermal equilibrium. We're observing synthesis of complex organic compounds at rates that would demand industrial-scale chemical reactors operating at impossible efficiency levels within these relatively small objects. Doctor, Chang's astrochemistry laboratory has been attempting to model the observed chemical processes using every known mechanism for molecular formation in space environments. Their computer simulations consistently fail to reproduce the observed molecular abundances and formation rates, even when incorporating exotic chemistry involving plasma interactions and radiation. The isotopic ratios in the produce-induced reactions d molecules show another disturbing pattern that violates principles of nucleosynthesis. Different objects are producing molecules with identical isotopic signatures that would normally require formation in identical stellar environments over similar timescales. This level of isotopic uniformity across objects that presumably originated in different stellar systems challenges our understanding of galactic chemical evolution. Mass spectrometry data from high-resolution spectroscopic observations reveals molecular species that shouldn't exist in natural astrophysical environments. Complex silicon-based polymers, exotic metal hydrides, and organic compounds with molecular weights exceeding anything found in natural comets are appearing simultaneously across multiple objects. The surface temperature distributions have evolved beyond anything explainable through passive solar heating. Infrared imaging shows temperature patterns that follow geometric designs, rather than the random thermal signatures expected from irregularly shaped objects with heterogeneous surface compositions. Thermal maps reveal hexagonal and spiral patterns in surface temperature that maintain their geometry as the objects rotate. These organized thermal structures require active heat distribution systems that would challenge our most sophisticated thermal management technologies. Yet they're operating on objects that should lack any internal energy sources. The power requirements for maintaining these thermal patterns exceed what solar energy input can provide by factors approaching infinity. The objects are somehow generating and distributing heat according to predetermined patterns that require computational control and active thermal regulation systems. Dr. Martinez's thermal modeling team has been unable to identify any natural mechanism that could produce the observed temperature distributions. Their simulations require assuming internal heat sources with power outputs equivalent to nuclear reactors, along with thermal distribution networks that would require advanced materials engineering. The acoustic properties detected through seismic monitoring of gravitational wave interactions suggest internal structures that don't match any known geological or crystalline formations. The objects ring like bells when subjected to gravitational wave impulses, producing acoustic signatures that indicate hollow chambers and geometric internal architectures. Ground-based gravitational wave detectors have been able to perform acoustic tomography of these objects by analyzing how they respond to gravitational wave pulses from external sources. The internal structure maps reveal cavities and chambers organized in patterns that suggest architectural design rather than random accretion or geological processes. The acoustic resonance frequencies follow mathematical relationships found in engineered structures designed for specific acoustic properties. The harmonic sequences match those used in advanced acoustic levitation and manipulation systems, suggesting internal architectures optimized for acoustic field control. Seismic analysis indicates that multiple objects share identical internal structural designs, despite their presumably independent formation histories. The acoustic signatures are so similar that they could serve as fingerprints identifying common manufacturing or formation processes that operated across different stellar systems. The rotation dynamics have achieved synchronization levels that violate conservation of angular momentum for isolated objects. All 17 objects now rotate as if they were components of a single rigid body, despite being separated by distances that should make such coordination impossible through any known coupling mechanism. The rotation axes have aligned to point toward common directions that precess in perfect synchrony as the formation orbits the Sun. This coordinated precession requires torque coupling across interplanetary distances through mechanisms that operate more efficiently than gravitational tidal forces by factors of millions. Radar observations show that surface features on different objects are maintaining fixed orientations relative to each other as they rotate. Crater patterns, ridge systems, and reflectivity variations are aligned across multiple bodies, as if they were painted markings on a single rotating structure rather than independent geological features. The rotational energy required to maintain this synchronization should dissipate through tidal friction and electromagnetic thousands of years. The fact interactions within that we're observing perfect synchronization suggests either recent activation of the coordination mechanisms or continuous energy input that maintains the synchronized motion against dissipative forces. Advanced computer modeling of rigid body dynamics has been unable to identify any classical mechanism that could maintain the observed rotational coordination. The models require assuming coupling forces that operate instantaneously across arbitrary distances, violating the fundamental principle that interactions cannot propagate faster than light speed. The magnetic field measurements have revealed the most disturbing development yet in our investigation. The 17 objects have created magnetic field structures that extend beyond the heliopause, connecting their coordination network to magnetic field lines that originate in interstellar space itself. These extended magnetic connections suggest that the clustering phenomenon might be part of a larger structure that spans light years rather than the astronomical units we initially assumed. The objects might be components in a vast network that extends far beyond our solar system, with coordination mechanisms that operate on galactic scales. Dr. Thompson's magnetosphere modeling team has detected magnetic field oscillations that propagate outward from the cluster at velocities that exceed light speed by measurable amounts. These faster-than-light magnetic signals challenge fundamental assumptions about electromagnetic field propagation and suggest physics that operates outside relativistic constraints. The magnetic field geometries show organization that would require superconducting materials operating at absolute zero temperature to maintain their current carrying capacity. Yet these fields exist in the plasma environment of interplanetary space, where thermal noise should destroy any superconducting effects within milliseconds. Space-based magnetometers have detected field reversals that occur simultaneously across the entire network, despite separation distances that should introduce propagation delays of hours or days. The instantaneous field changes suggest coordination mechanisms that operate through dimensions beyond the 3 spatial dimensions we normally experience. The quantum entanglement measurements have achieved correlation strength that exceed theoretical maximum values predicted by quantum mechanics. Bell inequality violations measured between different objects show correlation coefficients that approach impossible values, suggesting either measurement errors or physics beyond established quantum theory. Dr. Liu's quantum optics laboratory has been conducting these measurements using interferometry techniques that can detect quantum correlations across astronomical distances. Their results consistently show entanglement strengths that would require quantum information processing capabilities, operating at scales that dwarf any conceivable quantum computer. The quantum correlations persist despite environmental conditions that should destroy quantum coherence within nanoseconds. The objects are somehow maintaining quantum-entangled states across interplanetary distances, while embedded in the thermal and electromagnetic noise environment of the solar wind. These quantum effects appear to be strengthening as the objects approach perihelion, suggesting that proximity to the Sun somehow enhances whatever mechanisms maintain the quantum correlations. The scaling relationships indicate threshold behaviors where small environmental changes produce dramatic increases in quantum correlation strength. The implications force consideration of whether quantum mechanics might operate according to different rules in the unique conditions present during coordinated multi-body interactions on astronomical scales. We might be witnessing quantum phenomena that require entirely new theoretical frameworks to understand. International emergency sessions of the world's leading physics organizations have been convened to address observations that challenge multiple, fundamental principles simultaneously. The evidence suggests we're encountering phenomena that operate outside the boundaries of established physical law, requiring consideration of whether our current theories capture the full scope of natural processes. The philosophical implications extend beyond scientific methodology to encompass basic assumptions about the nature of reality and the relationship between observation and existence. If these phenomena represent natural processes, they suggest that nature operates according to principles we've never suspected and may not be capable of understanding within current conceptual frameworks. Dr. Anderson's committee has been tasked with developing protocols for studying phenomena that may not conform to traditional scientific assumptions about causality, locality, and the independence of distant events. The methodological challenges require maintaining experimental rigor while remaining open to possibilities that could necessitate fundamental revisions to scientific paradigms. Space law experts have begun examining the legal and ethical implications of potentially encountering organized systems that display characteristics traditionally associated with intelligence or technological control. The coordination mechanisms suggest information processing and decision-making capabilities that raise questions about classification and appropriate response protocols. The Vatican Observatory has issued statements acknowledging the profound theological implications of potentially discovering evidence for purposeful organization operating through natural processes on cosmic scales. The coordination mechanisms suggest principles of order that transcend random physical interactions, requiring new frameworks for understanding the relationship between natural law and intentional action. As October 15th dawns and 3i, Atlas continues its approach toward the October 30th perihelion encounter. Observational resources worldwide have been mobilized on a scale unprecedented in the history of astronomy. Every major telescope capable of solar system observations has been allocated emergency time to document phenomena that may represent humanity's first encounter with physics beyond established theory. The coordination between international observatories has created new models for scientific cooperation that transcend normal institutional and national boundaries. Real-time data sharing, synchronized observation schedules, and collaborative analysis efforts represent levels of cooperation driven by recognition that these phenomena require resources exceeding what any single institution can provide. Weather conditions at critical observatories have become matters of global security concern, with backup facilities prepared to assume essential observations if primary sites experience atmospheric interference. The redundancy reflects understanding that environmental conditions could determine whether we successfully document potentially once-in-a-millennium phenomena. The computational demands for processing continuous data streams from dozens of observatories, monitoring 17 simultaneously active objects, have required allocation of supercomputer resources, normally reserved for climate modeling and nuclear weapons research. The data processing challenges represent undertakings that require new approaches to information management and analysis. Artificial intelligence systems, originally developed for pattern recognition in other scientific domains, have been adapted to search for correlations in the clustering data that might escape human detection. These machine learning algorithms operate continuously, processing information at rates that exceed human analytical capabilities, while identifying anomalies that require expert interpretation. The amateur astronomy community has evolved into an essential component of the global observational network, providing measurements and analysis that complement professional efforts. Their flexibility and dedication enable continuous coverage that formal institutions cannot match, demonstrating the critical value of citizen science in addressing unprecedented phenomena. Social media platforms have become venues for real-time coordination of observational efforts and preliminary analysis sharing. Online communities process information faster than traditional scientific publication mechanisms, creating new models for collaborative investigation that accelerate the pace of discovery while maintaining scientific standards. The psychological impact on researchers confronting phenomena that challenge lifelong assumptions about reality has required expansion of support services at major observatories and universities. The combination of excitement and anxiety generated by potentially revolutionary discoveries has created stress levels that demand professional intervention to maintain research effectiveness. Public interest has reached levels that require sophisticated communication strategies to explain complex phenomena without generating panic or unrealistic expectations. Science museums and educational institutions worldwide have developed programs to inform audiences about the observations while maintaining appropriate uncertainty about their ultimate implications. Financial markets have begun factoring in potential technological applications based on whatever physics might be responsible for the observed coordination. While purely speculative, the possibility of revolutionary advances in propulsion, communication, and energy systems has attracted investment attention that could influence future research funding priorities, As perihelion approaches and the mystery deepens with each observation, the astronomical community finds itself documenting what may prove to be humanity's first direct encounter with phenomena that transcend the boundaries of known physics. The implications stretch beyond academic interest to encompass our fundamental understanding of how reality itself operates. The dance continues with mathematical precision that defies every assumption about independent objects following natural law. 17 visitors maintaining perfect coordination around an interstellar traveller whose properties challenge conventional classification, all operating according to principles that may require us to expand the very foundations of physical theory. Each night delivers revelations that simultaneously advance our knowledge and multiply the questions demanding answers. The gravitational lensing, the plasma circuits, the laser emissions, the quantum correlations, and the synchronized evolution all point toward coordination mechanisms that operate through principles completely outside our experience with natural systems. The mounting evidence suggests we're witnessing phenomena that may represent our first glimpse of physics beyond established theories. Whether these observations document extremely rare natural processes or reveal evidence for organization principles that transcend known physical law, the implications promise to transform our understanding of how the universe operates on every conceivable scale. As 3, Atlas approaches its closest encounter with our Sun, and its 17 companions continue their synchronized progression through the inner solar system, we stand positioned to witness discoveries that could echo through science for generations. The universe has challenged us with mysteries whose solutions may require fundamental revisions to our conception of natural law itself. The questions multiply with exponential urgency as each measurement reveals new layers of coordination that shouldn't be possible under any known mechanism. How do objects maintain such precise synchronization across distances where even light-speed communication should introduce delays that prevent coordinated action? What forces orchestrate such complex celestial choreography with mathematical perfection that exceeds our technological capabilities? The answers we uncover in the remaining days before perihelion may determine not just our understanding of this extraordinary event, but our comprehension of reality itself. The universe has presented us with phenomena that could reshape every assumption about existence, and time grows short for decoding their meaning before this unprecedented opportunity vanishes forever into the cosmic depths. The coordination has achieved levels that challenge the very concept of independent matter, operating according to local physical law. We may be witnessing our first direct evidence for collective behaviors that emerge when objects organize according to principles we've never imagined. Principles that could revolutionize our understanding of how complexity and coordination arise throughout the cosmos. The story of 3i Atlas and its mysterious companions continues unfolding, with revelations that push against the boundaries of known physics while operating with precision that mocks our most advanced technologies. Each measurement adds pieces to a puzzle whose complete picture may require us to expand our conception of what's possible in a universe that continues to surprise us with phenomena beyond our current imagination. The precision has reached levels that make veteran astronomers question whether they're witnessing natural phenomena or something that operates beyond the boundaries of established physics. As October 11th unfolds, the coordination between 3i Atlas and its 17 companions has evolved into patterns so mathematically exact that random chance becomes statistically impossible as an explanation. Dr. Sarah Chen's team at the California Institute of Technology has been monitoring what they're calling cascade events, where changes in 3i Atlas trigger identical responses across all 17 clustered objects within impossibly narrow time windows. When 3i Atlas showed a 2.3% increase in brightness at 1422 UTC on October 9th, 14 of its companions displayed precisely the same brightness enhancement within 6 minutes. The remaining 3 objects showed identical changes exactly 12 hours later, suggesting some form of delayed response mechanism that operates with clockwork precision. The mathematical relationships governing these responses follow patterns that would challenge our most sophisticated spacecraft coordination algorithms. Each object appears to know not just when to respond, but exactly how much to change its observable properties to maintain overall system harmony. This level of coordination requires real-time processing of environmental conditions and instant communication across distances measured in millions of kilometers. Ground-based spectroscopy has revealed another layer of impossibility that pushes us into territory where conventional astrophysics fails to provide explanations. The 17 objects are now displaying identical molecular emission signatures down to the isotopic level, showing chemical uniformity that should be impossible for bodies that presumably formed in different stellar environments under varying conditions. When the James Webb Space Telescope detected enhanced carbon monoxide emission from 3I Atlas at 8:15 UTC on October 10th, its companions began showing the same spectroscopic features within hours. But this isn't just similar chemistry, it's identical chemistry. The isotopic ratios, molecular excitation temperatures, and even the fine structure of spectral lines match with precision that would be difficult to achieve in carefully controlled laboratory conditions. Dr. Elena Rodriguez at the European Southern Observatory has been analysing these spectroscopic synchronizations with growing bewilderment. Natural comets develop their chemical signatures through billions of years of unique evolutionary history, exposure to different radiation environments, and interaction with varying stellar winds during their interstellar journeys. Finding such perfect chemical uniformity across multiple objects suggests either impossible coincidence or active chemical coordination through mechanisms we don't understand. The plasma dynamics surrounding these objects have evolved into configurations that violate fundamental principles of magnetohydrodynamics. The ionized gas clouds, or comas, that surround each object have begun forming interconnected structures that span the distances between them, creating what can only be described as a plasma network operating on interplanetary scales. Radio telescopes monitoring these plasma interactions have detected organized current flows that carry electrical power measured in gigawatts between the clustered objects. These aren't the chaotic electromagnetic phenomena typically associated with solar-wind interactions, but structured energy transfer systems that maintain stable operation despite the turbulent space environment. The Very Large Array in New Mexico has identified at least 23 distinct communication channels operating within this plasma network, carrying modulated signals that show clear information content. The data transmission rates exceed what Earth's entire telecommunications infrastructure could handle, suggesting information processing capabilities that dwarf our most advanced computer systems. Signal analysis reveals temporal patterns in these transmissions that follow mathematical sequences found only in sophisticated encryption protocols. The communication system adapts its frequency allocations and power levels in real time to compensate for changing orbital geometries, maintaining reliable data exchange as the objects move through their elliptical paths around the Sun. Dr. Michael Harrison's team at MIT has been attempting to decode these signals using advanced cryptographic analysis tools originally developed for intelligence applications. While the content remains undeciphered, the structural characteristics clearly indicate purposeful information exchange rather than random electromagnetic noise generated by natural plasma processes. As we stand at this pivotal moment in astronomical history, watching 3I Atlas and its 17 companions orchestrate their synchronized dance through our solar system, we're witnessing something that may forever change our understanding of what's possible in the universe. The mathematical precision, the electromagnetic networks, the gravitational anomalies, and the quantum correlations all point toward phenomena that transcend the boundaries of known physics. Whether we're documenting an extremely rare natural occurrence or discovering our first direct evidence for physics beyond current theories, the implications will echo through science for generations. The next few weeks leading to perihelion on October 30th promise revelations that could reshape our cosmic perspective entirely. The universe has challenged us with mysteries that demand we expand the very foundations of scientific knowledge. Time grows short for decoding their meaning before this unprecedented opportunity vanishes forever into the interstellar depths. The dance continues, and we remain captivated observers of what may prove to be humanity's first encounter with principles of reality we never dared imagine.